So, welcome back for day 5. The first thing we want to talk about today is a review of yesterday, where we introduced the initial list concepts before we move on to digging a little deeper into lists. I just want to see, did anyone have any trouble building this model? Does anyone have any questions over it? Did anyone not finish? Do you guys want to see the walkthrough for it? Where are we at with regards to this model?
I'm okay with the walkthrough.
Yeah, I'd like to see the list part. I mean, obviously the model part is easy, but
Yeah.
Yeah.
Okay, so is everyone in that same boat, ready to just do the walkthrough?
Sounds good.
Okay. So with this model, again, we're just sort of reinforcing the ideas that we discussed yesterday about the list. And it's basically just going to be a little bit more involved of an example compared to the little walkthrough version that I did yesterday at the end of the day. So we just got a couple of objects here. And again, the thing that we're going to be using the list for in this example is to help us manage our flow item flow in a little bit different way. Now, remember too, that the kinds of things that the list can do is pretty broad. And we're going to see that in the next example. And so really what we want to take away from this example are just like the basics of understanding the list interaction, where there are things on like one side of the equation that are pushed to the list, and then things on the other side of the equation that are pulled from the list. So just gonna set up, gonna make a few connections here. You might have noticed on the screen grab example of what the layout could look like, I didn't make any port connections between the queues and the processors, because if you're using a list, you don't even really need the port connections. In the example that I did yesterday, I did the port connections just so that you could see that, if you create ports and use a list as your flow mechanism, that the ports are basically inactive. And so if that's the case, you don't even really need to make them at all if you don't want to. All right, so I'm just going to go through and set up the model objects with a couple of like the simple things that we needed, like the arrival rate. We wanted to say the arrival rate was every 2.5 seconds. And we wanted to say that the send to port is going to just choose a random port. So we're just going to let the source send things randomly to our 3 queues here. Now, then in order to get the flow, and I also want to assign them their labels. So on creation, we will say set label and color. And this is just using the default options here. So if we see where we're at right now, right, we just should see a random collection of flow items going into these queues. And that's pretty much what we're looking for so far. So nothing too different from anything we've done so far this week, but again, just sort of taking this incremental approach where we try out a little bit of what the model needs to do and test it to make sure it does what we expect before moving on to something else. So the next thing that we need to focus on is using the list. So the first thing I need to do is just to add a list to this model. So I'm going to come up to my toolbox, go to the green plus sign, and make a global list that is an item list. So this adds the list to my toolbox, and now I can determine events in my model where flow items will be pushed to this list, because this is an item list, and in an event on the processors where they will try to pull flow items from this list. So I'm going to push to the list by using the send to port event of the queues. And notice that I control clicked on each of these objects to make them a selected set of objects. So remember this from yesterday. This gives me some capabilities of editing multiple objects at the same time. And so if I have a selected set of objects and then come over to an event like send to port in the properties panel, I can say that I want to use a list and push to the item list, and that will allow all 3 of those objects, where it says 3 objects changed, that will allow all 3 of these objects now to be pushed into the same list. So rather than having to go to each object individually, I can set it up all at once using this selected set of objects capability. And then when I'm done working with the objects as a selected set, I can just shift click and put them back to normal. Now, if we, again, just kind of see where things stand right now, if I open my list entries on the global list, and we just kind of watch what's going on here. Now, not only do we have flow items being sent to the queues, that's also causing those flow items to be pushed onto this list, which makes them available for something else to pull them from a list. So remember that at the core, a list needs two sets of participants, where we have, on the one hand, things that are being pushed to the list, and now that's what we have with the flow items. And then we need to set up another set or another group of entities in the model that will function as pullers from the list. And the purpose of the list here is in this example, is going to cause flow items to flow to their pullers. But in the like in the core concept of the list, a puller just means that something is searching the list, and when it finds the thing that it's looking for, it takes that thing off of the list and facilitates some other modeling action. So because I'm going to set up the processors as being pullers, the result of the pull is going to be not only to remove the flow items from the list, but also to cause the flow item to go to the processor that pulled it. And so again, I can set this up for all the processors at once. If I do a shift drag around all the processors, click on one of them, and then under the input section, the first thing that I'll do is say that I want to activate pulling for this processor. And you might have seen there that it said 4 objects changed. So now all 4 of these objects are now ready to start pulling, but their pull strategy needs to be set to look at my list. So instead of the pull strategy saying that I can pull from any port, we want to set the pull strategy to say that we are using our list, and we're going to use the pull capability to say that we are going to pull from our item list. And again, when I click off of that, it says 4 objects changed, because now all 4 of these objects are pulling from the list. Everyone okay with that so far? Okay, so again, if we just kind of see what this looks like right now, if we hit reset and run, flow items now will only be in the queue, and their entries will only show up on the list if the processors are all busy. And right now, all these processors are just able to pull the first available box that they can find. So whatever box is newest on the list, that is going to be the flow item that the processors pull. Because right now our arrival rate is such that the processors are idle, not in infrequent amount of time, right? We're not seeing a ton of buildup in the queues right now. Okay, now in the challenge section for this model, we wanted to be a little bit more specific about what kinds of flow items our processors are able to pull. And we want to use the filtering capability of pulling from a list, or the where query, that allows us to differentiate what each processor receives based on the type of flow item. So if I want processor 1, for example, to only pull things that are type 1, I can come back to my pull strategy, expose the query input field, and use my query builder to say, I want to pull things where type is equal to 1. And so processor 1 now would only pull things where type is equal to 1. If I go to processor 2, I can do something similar, where I say that I want to pull where type, and then I can just fill in my criteria where it says I want to pull things where type is 2. And then for processor 3, we'll say that we want things where type is equal to 3. And then on the 4th processor, we wanted to do something a little bit more interesting. We wanted to say that processor 4 can take things that are either type 1 or type 3. So if I go back to my my processor, go to the pull strategy, and then in my query field, I can say where type is equal to 1. And that's good enough to make sure that processor 1 pulls things that are type 1. Now, very similarly to what we saw yesterday with the selection criteria for a zone subset, I can also have things like or and in here. So if I say or, remember that this is evaluating each flow item individually, where it's saying, okay, here's a flow item that's on the list. Is its type equal to 1? If yes, you can pull it. If not, also check to see if its type is equal to 3. And if it is, then go ahead and pull it. If the flow item that we're evaluating on the list is neither type 1 nor type 3, then we just ignore it and we leave it on the list for someone else to pull. So remember that the whole idea behind a query is to allow you to establish a set of search criteria that says these are the things that I'm looking for, right? And so now when we run this, we'll see red box is always on processor 1, green box is always on processor 2, blue box is always on processor 3, and red or blue boxes on processor 4. And so the queuing that we see is for whatever parts are essentially waiting for a puller. So what's kind of interesting about the way this one works is that we're going to see kind of an abundance of green boxes, type 2 boxes, because only processor 2 is working with the green boxes. But since we have kind of like 1.5 processors for the red and the blue boxes, they tend to not spend as much time in the queues, right? Because red boxes are dedicated to processor 1 and blue boxes dedicated to processor 3. And then processor 4 can also take 1s or 3s. So it's like type 1 and 3 are sharing that second processor, which is enough to keep their queuing pretty low out of the queues. So we tend to see more green boxes accumulating because only one processor is dealing with the green boxes.
I got a question.
Yeah.
On the list query,
Mhm.
Can you only reference things on the list query that are on the list, or can you add other elements from the model? For example, if we had another processor in between 1 and 4, in between the queues, and we wanted to say you could go type 1 or type 3, and also went through processor 5 or whatever to get to processor number 4.
Okay, so remember that the list query here is as if the processor is asking the question of the list, right? So this query is essentially saying processor 4 is only looking for things that look like this, type 1 or type 3. And the list queries are also only able to query fields that are on the list. So if there is some data that you want to query, it has to be associated with an entry on the list.
So you'd have to push it there. You'd have to push like what processor did it go to or something?
Yeah. Yeah. Anything that you want to know about has to be made available to the list.
Got it.
So like, remember that when we're looking at one of these rows in the list, right, this is all the information that is related to this unique box inside of Q2, right? So it has its type, it's got its age, its distance, its queue size, and you can add whatever other important fields there are as well. Like maybe you want to pull things whose like first process was it like processor A, and you're saying, I want things on the list that are this type and use this particular machine as their second process. So you'd have to include that as part of the field data on the list that you potentially may want to query.
Got it.
Yeah, that's a good question. Yeah, so yes, the information on the list is, or rather the information associated with the entries on the list is largely in your hands. We do include some common data points just by default, but you can always add custom fields to enhance the kind of information that you want to be able to query with.
Hey, Regan.
Yeah.
Question. Following up to what the previous question was, I started thinking about a possibility where all those green boxes are piling up in the queues. What if you wanted to add a condition where in a situation where you have a critical number of green boxes backing up, the fourth processor might be able to accommodate them? Something like that. It's kind of a follow-up to the previous question about adding another condition, if you will, to your query capability.
Yeah, I mean, the kinds of expressions that you can put into the query field can get pretty interesting. And I believe there are SQL definitions for doing like ifs, then else kinds of things as part of your query. I've never actually had to do that, but I know that there are things to do that in the SQL language, and I think we did implement them. So in theory, yeah, you could have conditional parts of a query where you could say, if there are this many green boxes on the list, then I want to be able to grab those as well.
Yeah, I guess what I'm thinking here is a little bit more direct, since you mentioned that a list query is querying factors or characteristics of the list itself. So I'm looking at possibly age there. Let's say if something gets to be of age that's just astronomical past a limit like that. I guess I'm looking at one that has 599 on it there. It's your first entry, or your maybe one of the original entries. It seems to me that you might be able to say, okay, if my age goes above 600, I'm going to go ahead and have processor 4 process that dude, and as kind of a an exception situation.
Yeah, that sort of thing is actually fairly easy to do with an order by clause on the query.
Okay.
Where you could say that you want to order by, and this is a little bit, I'll just type it out here. Just so if you were to say like order by, and then say age greater than or equal to 600, DESC, like that. So this is an order by query that allows you to say that if there are things whose age is greater than or equal to 600, we want to sort them to the top of the list. So in the event that there are, like here, your first thing is, okay, I'm only going to consider things that meet this criteria, right? And then for those things, if there is anything that meets this criteria, where their age is greater than 600, then they get prioritized to the top of the list. They would become the first thing that I would pull.
Okay.
Now that doesn't help us in this case because this happens to be a type 2 thing with a high age. So you would need to include another thing that said that you could also potentially take these, but only in this case. Does that make sense? And that's a little bit more complex a query, and I'd have to think about exactly how to do that.
Thank you.
Could you put or just put another or statement, or age greater than 600?
If you did it as a filter, yeah, I mean, because like you did something like this, where we say, okay, where type is equal to 1 or 3, that's your first condition. Say, or where age is greater than or equal to 600. So this would be a way of saying, okay, if there's nothing, if there are these things, then that's like the first thing that you want to consider taking. And then if this fails, you would check this filter condition where you say, okay, if there's anything that's old on the list, whatever I define as old, then consider taking those as well. But again, then you would need the order by to say, well, maybe you could even just like order the age part first. If you did that check before you did this check, that might work, because the order in which you put things into the query matter, right? Because it's whatever gets evaluated first kind of wins. You know what I mean?
Yeah, so in following up to that, you're kind of excluding type 2 if there's ever a type 1 or 3, regardless of its age, the way you've got it written. But what you just said was, if you put the age condition first, it takes priority, presumably, if I understand you correctly.
Yeah, so if we have that in there, so the query now that we're running on this says, I want things that are old or things that are type 1 or type 3. And so right now we're getting things that are type 1 and type 3 because there's nothing that's old on the list, right?
Right.
And so now we're waiting for one of these green boxes to get old, and we'll see if that gets pulled by processor 4. So we'll just speed things up a bit here. We'll see if something gets old, if we see a green box go by at 600 age or more, right? So we're at 400. I guess I could have used a smaller threshold, but just since we were talking about that, now we're approaching 500. So yeah, there's a green box. Green boxes went by that were old, and then we're back to just taking the blue and red boxes. So that actually worked out pretty well.
Awesome. Good job.
Yeah, so whoever had that idea, I didn't see who was talking at the time, but good job. That's a much simpler way of thinking about it than what I was thinking. But yeah, that's the nice thing about working with lists, though, right? Is you can have these kinds of search conditions that allow you to do some pretty cool things about, these are the sorts of things that I'm looking for, and this is the order in which I'm looking for them. Hey, any questions then so far on anything list related or anything like that to this point?
Quick question. You brought that entries window up pretty quickly. How did you get that?
That's going to the list in the toolbox, right clicking on it, and you get the option to view entries or back orders.
Wow. Thank you. Thank you.
Okay, so like I mentioned yesterday when we first started talking about this stuff, this is really a really simple but highly visual application of using a list, which is the reason why I like introducing this part first, because seeing the flow items move to object based on what the objects are looking for, not only is that something that actually does come up every once in a while, but it's a nice visual way of understanding that on the one hand, again, we have things that are getting pushed to the list. And on the other hand, we have things that are pulling from the list. But as far as like the model result where we're seeing flow items flow, that's a fairly simple idea. It is one of the ways in which the list can be used, but it is just one of the many ways. So in the next section that we're going to talk about with regards to the list, we are going to talk about the list in its more powerful application, which is pretty much where the list was born, which is in process flow. So the list is natively a process flow tool. We created the global list because they were turning into such a useful thing that we thought, well, we should make these a little bit more easily to access, a little more easily accessible, excuse me, from the object side. But in the process flow environment is really where the list starts to get really interesting. Now, the list is one of our shared assets, which means that it has a lot of shared functionality with the other two shared assets that we've seen so far, like the resource and the zone. And in fact, a lot of things about the resource and the zone can be done by the list as well. And the resource and the zone are just ways of making that kind of behavior more easily accessible. So you can kind of think of the list as like the big shared asset that can do just about anything, and the resource and the zone are just more specific implementations of that. That's not terribly important, but I think it's an interesting thing to think about, where there's going to be a lot of overlap between the different shared assets. And so the question about like, well, how do I know when to use a resource, a zone, or a list? It kind of depends, right? Because if you wanted to, you could use a list for almost everything that you needed to do with regards to a resource in the zone. But there is going to be times when the resource in the zone might just give you an easier way to do some of this stuff. So let's talk about how to use the list in its process flow capabilities. So I'm just going to make a new model here. We'll move away from what we're working on. And I'm going to make a general flow. And let's start just by seeing in the shared asset library that we have the list shared asset, an activity that allows us to push things to a list, and an activity that allows us to pull things from a list. So let's build a couple of simple little activities just so that we can kind of see what's going on here. So this is just going to be a couple of, simple little things where I have a source and then a delay, and then I'm going to say that we're going to push to a list. And then after that push to list, I'm just going to put in another delay. And then a sync. Now, notice when you click on the push to list activity, it doesn't know what list to push to. That's what the exclamation point here means. So we need to give this activity a list to look at so that we can push things. Now, one of the ways in which we are going to do things differently in process flow compared to what we did in the other examples with the 3D model, rather than going to the toolbox and creating a global list, we're going to come to the shared asset library and just create a shared asset list. So what's the difference between these? Well, the main difference is that this list is considered local to the process flow environment, which means that objects don't have the ability to push or pull from this list, because this is a list that only is accessible from within process flow. And you can see here, it says that it's using its own little internal list. It's not a global list, it is a local list. In a later example, I'm hoping I'll be able to show you when you could have interactions between process flow and the object environment using global lists and shared asset lists, because I think it's a good thing to know about. But for right now, just notice that by default, a process flow shared asset list is local to the process flow environment. Okay, and because we have the exclamation point on the push to list activity, we need to associate this push with this list. So I'm going to do that right now just by using the eyedropper, clicking on it, and we can see that blue line that tells us that this is the list that we're pushing to. Okay, now if I just run the model, I want you to notice how the tokens flow. So they go through the delay like they would normally. And now they're coming to the push to list activity, and they're not allowed to continue. And we can see the green dot number over here that tells us how many entries there are on this list right now. So if we go to the list properties and say view entries, this is giving me, again, that table view of the entries that I have on the list. And notice here that we have a value that says that the pushed value on the list are all of these tokens. Notice that there are no fields on this list, because by default, the process flow list, if you go to advanced, it doesn't have any fields predefined. So if there's any like special data that you want to be available during a pull, it'd be your responsibility to add that as a field on the list. But for right now, we're not going to worry about that. Okay, so with what we're seeing right now with these tokens that are accumulating at the push to list activity and they're becoming entries on the list, this is very similar to what we saw in our previous examples when flow items were being sent to a queue and they weren't allowed to continue to flow, but they were accumulating in those queues and they were also pushing themselves onto a list. Same idea here, where entries on the list with no pullers just sit where they are in their flow, waiting for something to pull them. So that means that if I want these tokens to be able to leave the push to list activity and do whatever comes after the push to list activity, it is up to me to put in a pulling event that says that we can pull these tokens off of the list. Okay, so let's hit reset and let's bring out a pull from list activity. And notice that it automatically linked itself up to this list. Okay, so we have a pull from list activity, which is nice. But if we run the model again, notice that same thing happens. The tokens come to the push to list activity. They become entries on the list. But still nothing is pulled because nothing is actually causing this pull from list activity to happen. Right? We need a token over here that will cause the pull to take place. So again, this speaks to the core idea that we talked about yesterday about the list, where we need two sets of participants interacting with the list. Right now, we have one set of participants. We have these tokens that are being pushed to this list. So if I want to pull these tokens from this list, I need a different set of tokens that can pull from that list. Because I need someone over here that causes this pull event to happen. Okay, so let's create another set of tokens as well here. So let's say that we've got another source and another delay, just so you can see the tokens before they actually get to the pull from list activity. And then we're going to link those here. And then we're going to bring in another delay. And then bring in the sync. So now when we run, notice on the right-hand side now, I'm creating different tokens. So we have one set of tokens over here on the left, one set of tokens over here on the right. And when the first token gets to the pull from list activity, and we're going to get a few over here, they are represented by the red dot number on the list. And that red dot number indicates back orders. So if you were to come to the list properties and say view back orders, then I can see that I have a back order on the list that says that the token that is named ID6 is requesting one thing from the list, and it requires one thing from the list, and it is 0 fulfilled, which means it is a back order. Now also notice that I stopped the model right when two tokens stopped interacting with the list, where I have one token over here that has moved on from the push to list activity and a token over here that has moved on from the pull from list activity. That's because this token searched the list and it found this token, which caused it to be pulled. Now in process flow, that allows the pulling token to continue on to some other set of activities. And that allows the pulled token to move on to another set of activities. And so in process flow, defining what happens when a pull takes place is up to you. With the examples that we did in the 3D model, the act of pulling from the list caused something to happen. It moved a flow item from one object to another. In process flow, all it causes is the token to be released from its list interaction activity and continue their flow to some other activity that happens next. So that means that the list interaction is like a gatekeeper about saying that you can't continue to some next logical event until you're either pulled from the list or until you pull something from the list. Again, highlighting this independent actor nature between the two sets of participants, where the tokens on the right want to do something, tokens on the left want to do something. And when they interact with each other on the list, that becomes a point where they need access to each other before they're allowed to continue. Okay, so if we just watch this continue for a while, again, just kind of notice that pattern where the tokens on the left-hand side that are destined to become entries on the list are pushed to the list like our flow items were. And the tokens on the right-hand side of this flow represent our pullers. And when they get to the pull from list activity, they're basically looking at the list and they're saying, is there anything over there that I could pull? And the things on the left-hand side are coming to the list and saying, well, now I have to wait here until someone pulls me from the list. And so with the way it's set up right now, one puller gets one entry from the list. So let's take a look at some of the properties available to us here on the push and the pull from list activity, because there's a bit going on. One of the first things I want to point out is that both the push to list activity and the pull from list activity have an input property that says assign to. So here we're saying assign to token.puller, and over here on the pull from list activity, it says, whoops, that our assign to says token.pulled. Now, remember, we said that any activity that has this kind of an assign to mechanism means that we're going to be assigning labels. So when we are assigning labels, we're assigning a label to the token that is here at this activity, and the name of that label is going to be puller. But what is the data that's actually being assigned here? Well, let's take a look at what happens when we get a pull to take place again. So we'll get our back orders to the list first, and then we'll get our first entry that gets sent to the list, and they're going to get pulled. So right about there. Now, if we take a look at the token on the left-hand side, this token was an entry on the list. It's been released from the pull from list, and now it's at the delay. And if you click on it and look at its labels, it says that it has a label now that says puller ID 1. So first of all, the reason why the label is called puller is because this token is going to keep track of who pulled this token from the list. So this token is essentially saying that my puller, the guy that released me from the list, is token ID 1. That is a pointer or a reference that allows us to potentially communicate with the puller of this token. Now on the other side, we'll take a look at this token, and it says that I am token ID 1, and my pulled label says that I pulled token ID 8. And then again, this is a reference to the token that was pulled by this particular token, so that we can potentially communicate or have access with the data stored on ID 8. So one of the things that we do here with the process flow activities is that we allow the tokens that are pulling to know what things they pulled, and we allow the tokens that were pushed to know who they were pulled by. So that's why on the push list activity, the label is called puller, because we're saying that my puller was that guy. And over here on the pull from list activity, we're saying that the thing that I pulled is that guy. And again, as is the case with any of these activities where we are assigning a label like this, you're free to change the name if it helps you understand better what these different label names mean. Because sometimes, especially the first time you see it, the difference between puller and pulled, they're really similar to each other, depending on the point of view that you're thinking of. So remember that this token, who was a puller from the list, is keeping track of the thing that it pulled. I want to know, who did I pull from the list? And this token over here that was pushed wants to know, who was my puller? How did I leave the list? I left the list because this token is my puller. Does that make sense so far?
Question, does the insert in front of even apply here?
Yeah, it does. Yeah.
Okay,
The insert at front of would be a way to say that, like, if this token interacted with multiple lists, right? Where it gets pushed to a list here, and then later on it gets pushed to another list. Insert at front of would allow you to keep track of a record of all of your pullers, because insert at front of would say that, okay, the first time that you were pulled, you were pulled by token ID 1, and then at another point you might have another push to list that says insert at front of. And that would allow you to say that I don't want to lose access to my original puller, but I want to add another puller to my record of pullers. So it only comes into play if you have the same token potentially being pushed to new lists at various points in the flow, which is very, very possible. And you want to keep track of a record of all of your pullers. So that would build in an array of potential, or rather an array of your pullers, of the pullers that you interacted with over the course of your flow. Same thing on the pull from list side, where if this one token needed to pull multiple times from different lists as they progress, you might use insert at front of to keep a record of all of the things that you pulled over the course of your flow. Okay, so that's kind of one of the first big things, is that pullers and entries know who they interacted with on the list. And one thing that we're going to see in a little bit is that is actually fairly important, because when we start pulling things from the list, a lot of times we want to make decisions based on who our puller was, or make decisions based on what I pulled. And we need to be able to have access to that information. Now, one thing to take note of with the way this model is set up, I actually did something here that could potentially cause a problem depending on what other things my model needs to do. And so I'm going to let the model continue, and then I'm going to show you what that is. So we get to a point there where that token finished the delay and it went to a sync. And so that token is now gone, right? If we take a look back at this token, notice that it says, okay, my pulled information now says that I have no path. Remember that last time we looked at it, it said that we pulled token ID 8, but now it says no path because the token that you pulled no longer exists. It went to a sync. So that's something to watch out for, because if this token needs to do something based on knowing something about its pulled counterpart, then if it goes to a sync before it has a chance to do that, then you may not have access to that data anymore, because the thing that you pulled might have left the model because it went off and did its own thing. Now, that's not always a problem, but it is something to be aware of, that if the thing that you pulled goes to a sync or is otherwise destroyed out of the model, you won't have access to it anymore. And we show that by saying that your pulled no longer has a path. Okay, so that's the first big important idea, this idea of assign to on both pushing and pulling, and how that affects the label data of those tokens. Now, another really important option that we want to take a look at relates to what we can do with the pull from list activity. And one thing that I'll point out here too is that the pull from list activity has probably the most options of any single activity in the library, which makes it a little bit intimidating, because it can do so many different things. And we're not going to talk about all of these options, but I do want to hit on a couple of the really important ones. If you want more information about what these different options of the pull from list activity do, I'd invite you to click on the green question mark in the upper right-hand corner of the activity properties to open the manual where it discusses all of this. And also in the walkthrough directory of the download materials, there is a list walkthrough model that demonstrates how to do, or rather how to use and see the effect of all these different all these different options. So you can read about it in the manual, and you can also see the walkthrough model that will actually show you examples of it. But for now, the first option that I want to draw your attention to is this idea of a request and a require number. So in the pull from list activity, we have the ability to indicate how many entries from the list a given puller would like to pull. And we do that with the request and require value. So right now, the request and require values are both set to 1, which means that each puller will pull at least, well, rather I should rephrase that, sorry, that each puller will pull exactly 1 entry from the list. Okay, so that means 1 puller takes 1 entry. It's a 1-to-1 ratio of entry or of pullers and entries. Now, if we were to set the request value to say 3, and also our require value to 3, this means that we're going to pull that each 1 puller is going to pull exactly 3 entries off the list. So let's just see what that looks like. So if we hit reset and run, so we get our first puller on the list. And I'm going to click on it just so that we can visually see it. So there's our puller waiting for something to pull. And here comes the first token that it pulls. Now notice that the puller is still on the list, and this token is moved on, and it says I was pulled by token ID 1. But because each of these pullers is waiting to pull exactly 3 things, because that's what the request and the require values say to do, then they remain back orders on the list as they wait to pull other things from the list. So here comes the second one. And also notice that over in the back order queue, we have the back order queue showing where it says that token ID 1 has requested 3, it requires 3, and we are now 2 fulfilled. So with 1 more token, this back order is allowed to pull 1 more thing from the list. So again, that token goes to the delay, and it says I was pulled by token ID 1. And so now we're waiting for another one. And so now notice that token ID 1 is no longer in the back order queue because it fulfilled all 3 of the things that it requested and required. And if you click on this token now, it says I have an array of the things that I pulled. The first thing that I pulled doesn't exist anymore. That's what the 0x0 here means. It's just like no path, because that token actually went to the sync before the pull was complete. But I can also see that I pulled token ID 9 and also token ID 10. So the things that I pulled, there are 3. 1 of them doesn't exist anymore, and the other 2 are these token references. So that means that the puller stayed on the list, stayed in the backorder queue, waiting for the ability to pull all 3 of the things that it wants. So this means that if the request value and the require value are exactly the same, in order for the puller to consider the pull operation a success, we had to pull all 3 of these entries. Okay, so under what circumstances then might you have a different value for request and require? Well, if we mouse over the input property for request, it says how many entries to try and pull from the list. Okay, reasonable. And then if you look at require, it says the minimum number of entries to pull from the list. So that's interesting. If you have a higher value for your request, that would indicate the maximum number of entries you want to take from the list. But if I were to put in a lower value for require, then that would tell me a minimum. So now with this arrangement, a pull is considered successful if you pull anywhere between 1 and 3 entries from the list. So if you run this now, again, we get our first puller to the backorder queue, and we're waiting for our first entry to arrive. And there, the puller is released from the list and says, yep, I pulled my one thing, ID 8, and I was pulled by ID 1. And again, that's because pulling one entry is considered a successful pull with this arrangement of request and require values. Since we could pull at least one thing, we're not going to wait around for the other two. We're good to go. So that means now that if we ever have more entries than we have pullers, we might see some tokens, some pullers pull more than one entry from the list, but only if there are a lot of backorder, or rather a lot of entries already there. It's like, here's an entry, and then another backorder came and they just pulled because one was good enough. So here's an entry that comes in there, and then another puller is going to come that's going to take that off the list because one is good enough. Now we have a bunch of back orders, and each of those back orders is going to pull just one thing because there is only those one things on the list, and we still have more back orders because we are again saying that we can pull at least one thing, but up to 3 things. So with the way this model is set up right now, we're going to have a hard time seeing a puller pull more than one thing because we have more back orders right now than we do entries. But if we were to say trade sources so that this source now creates the tokens that get pushed to the list, so here's a, okay, so again, that was a 1-to-1 pull. Another 1-to-1 pull. I have a hard time getting to the point where I have, okay, so there's 2 entries, finally. 2 entries on the list. And now we have one puller that's about to come to the list. Oh, 3 entries now. And so when we step through to the next event, here's our puller. It's going to look at the list. It's going to say, I would like to take between 1 and 3 things. That means that this one puller gets to release all 3 tokens from the push to list. And if we look at his labels, he says, these are the 3 things that I pulled. I got token ID 30, 32, and 27. And again, that's also considered a successful pull because it's within the range defined by the require value and the request value. Okay, any questions at all? Okay. So let me set the request and require values. I'm just going to set them to 2. So this is just going to make it so that one puller can pull multiple entries. And I want to show you what happens if there are, again, because we haven't talked about queries at all in this context. Queries work pretty much exactly the same way. But there's some cool things that we can do with queries in process flow to make things a little bit easier to set up. So let's just say that I have like a label over here. We're going to assign some labels there for the entries, and we're going to assign some labels over here. Let's say that this label, I'm going to call this the entry type to define the type of entry. And I'm just going to assign this using a set of percentages. We'll have 3 types, and we'll say that we've got 40, 30, and 30. And those are types 1, 2, and 3. And then over here on my other assigned labels, I'm going to say this is my puller type. And my value also by percentages, but maybe got 20% for a 1, 35% for a 2, and 45% for 3. Okay, so the pullers have their own label with their own distribution of values. The entries that are going to be on the list have their own distribution of values. And let's do something kind of simple where we want the tokens on the right to pull something that has the same label value as they do. So in your query, you can say something like, well, I'm looking on the list where. Now, notice something that's kind of cool here. We didn't set up any fields on the list. Like if you come back to the advanced options, remember we said that we have these fields that we can query. And in the global list, we had to query fields. But in process flow, we let you query any label on the tokens that are being pushed to the list. So if you go to the where section of the query builder, it says, well, do you want to query the entry type or the puller type? Now, unfortunately here, it doesn't know the difference between labels that are on the tokens on the left-hand flow or the right-hand flow. It just says, these are all the labels that I see in your model. Which of these would you like to query? Well, remember that the query is from the point of view of the puller that is looking for something that is on the list. So that means that if I want to use this where it says where entry type, I have to make sure that entry type is a label that exists on the tokens that are being pushed to the list. So if I say where entry type, then that would mean that I'm looking that each puller, with the way this is currently set up, is looking for things where the entry type is less than 10. Right. And so since my label values are 1, 2, 3, everything is less than 10. But if you were to say like equal to 1, like we did in the previous examples, this would mean that all the pullers would only pull things where the entry type is set to a 1. Because this query is going to be executed by each puller that comes to the pull from list activity. Now, one thing that's kind of cool that you can do here in the query is that there is a keyword you can use called puller that gives you access to the token that is pulling from the list. And then using the dot operation, you can access labels that are on that puller. So if I say puller dot puller type, this is a way for me to say that I want to only consider things on the list where the entry type is the same as the puller's puller type. Okay, and again, we can do that because there's a keyword available in the query field puller, which refers to information that is stored on the puller token. So notice here that I can't do token dot puller type. I can't do that, but I can say puller dot puller type. And that'll work because the puller is indicated as being the token down here. And so any information associated with the puller, I can access using the dot operation to get things like label values. And so this means that only tokens that are of the same type are going to be pulled because we're saying that the entry type is filtered based on the puller type. So if we watch this run for a second, we might see that we have some entries that are coming to the list. And in fact, let me, for some reason, my entries thing got messed up there. And so if we take a look at this token, we see, okay, I'm entry type 1, token over here, I'm entry type 2. So that's why we have a back order and an entry on the list at the same time, because this token is looking for something whose entry type would be a 2, because it says, again, my query is, I look for things on the list that are the same type as me. And so only when something shows up that is the right type, so this one says, okay, I'm puller type 3. So here something got pulled because it says, okay, I'm entry type 1. I was pulled by token ID 11. I am entry type 3. I was pulled by token ID 8. So ID 8 right here, or not there. Where's ID 8? There's ID 8. It says I'm puller type 3. I'm pulling 2 things. So I'm waiting for one more thing of the appropriate type. And so this guy says, I pulled 2 things. I'm puller type 1. I pulled token ID 6, and the other thing that I pulled has been removed from the model already. So I don't know what token that is anymore. Okay, now visually, this is kind of hard to follow. So in the past, we would say, well, let's assign colors maybe to these to these tokens. But if you go to the more property section and go to where it says visualization, the token colors will only let me choose one label as the means to assign labels. So like if I have 2 different labels like entry type and puller type, I can only set the colors for one of them. So I either have to make sure that both sets of tokens use the same label name, like maybe just type, or I need to use a different mechanism for coloring the flow items, which you can do. Like, for example, I could bring out a change visual activity, put it here. We'll do that on the other side as well. I could say that I want to set object color, like maybe set object color by case. And the value is going to be to use the entry type label, and the object is just the token. And then I can choose my colors. Like maybe I say red, green, and blue. Right, where I want to use this label as the key for deciding my colors. The token is going to receive the color, and then the colors that I choose are whatever colors I want based on cases 1, 2, 3. And I can do the same thing over here. I say set object color by case. But on this side, it would be the puller type, because we have the puller tokens on this side. The object is still the token. And then I can do the same colors to match up with the other cases on the other side. And then when you run it, you'll see that only light colored tokens will pull each other. So there's a green and the red, so we know they don't match. Got a couple of blues. Those blue ones will be waiting for a while because we don't have any blue entries on the way. We can see we've got like some red pullers, and we have some red entries coming up. So those will be pulled. Okay, does that make sense so far? Okay, so this thing that we did in the query where we were able to access the information stored on the puller, where we're saying that we want to pull things where entry type is the same as the puller's type. That's a good thing to know how to do, but there's actually an easier way to do something like this, where you want to do a straight matching operation between a value that's being carried by the puller and a value that's being carried by the entrant. So I'm going to actually remove this query. And the other way that you can do that same thing is by using what's called a partition ID. So again, kind of similar to what we talked about yesterday with the zone, where we can set up these different partitions on the list, where you can say that my puller only considers tokens that are in a partition that have the same value as my puller type. So if I say that the partition ID here is the puller type, that means that the puller will only look into a partition of the list where tokens with these values, whatever values there are for puller type, are located. So remember, the idea behind a partition, similar to what we talked about with the zone, is to create segments or subpopulations within a shared asset. In this case, we're talking about it with a list, where we want to organize all of the tokens into partitions. Now, if your puller is looking at a partition ID, then that means that your entries also have to be looking at a partition ID. Because right now, and again, I'll open up my view entries and my view back orders so that we can see this. If I run the model right now, you're going to see that the back orders are going to be segmented into partitions. So here is partition ID 2, where pullers of ID 2 are going to be located. Here's partition ID 3, where pullers of ID 3 are going to be located, and also ID 1. But now notice that in the entries, there's a partition ID called 0x0, or what we call the null partition. And in the model, nothing is getting pulled, because my partitioning mechanism means that a given puller will only look at the partition ID that is the same as its partition ID. And so the only partition in the entries of the list right now is this null partition, which means that partition tokens ID 1, 2, and 3 can't actually see these as valid entries to pull. Because these tokens are actually in a different partition. These tokens are looking in partition ID 2. These tokens are looking at partition ID 3, and these are looking at ID 1. But the entries on the list are not segmented into those partitions. So like I said, that means that my entries also need to be told to be pushed into a partition. So I'm going to go to the partition ID here and say that you are going to be pushed into a partition ID that is the same as your entry type. And so now when I watch the model run, I'll have back orders that are looking at partitions on the list, and I'll also have tokens that are occupying partitions of the list. So you can see like here's partition ID 1. This token is in partition 1. That's that guy right there. And I currently don't have any back orders in partition ID 1. But as soon as I do get one, it is going to release that token from the list. So this is the same result as doing the query where I said that the entry type label has to be a match for the puller's puller type label, but it allows me to do it without including that as part of my query. This is doing like a first order elimination where it says, okay, I'm not even going to look at other things in the list unless they're occupying the partition that I'm looking at. Right? Where I'm saying I'm looking at this partition, and these are saying I am being put into this partition. And so now I don't need to have a query to do that because the partition ID mechanism is going to do that for me. And so the partitioning mechanism could potentially help you simplify certain kinds of queries where if you were saying that the the puller and the entry had to share a value that had like some value in common, the partitioning scheme is a good way to do that without having to include it in your query. It makes your queries a little bit simpler because you don't have to include that first order elimination to exclude things that don't match the particular value that you're looking for. Okay, any questions there at all? Okay, so now having spent like a ton of time talking about lists, we're just gonna put that aside for a second to quickly talk about another important idea that I want to introduce in this example. And that's thinking about different ways of affecting arrivals in your model. So just really briefly want to go over an activity that we haven't talked about yet, but I think is pretty important, which is called the scheduled source, which allows you to define a schedule of arrivals using a table interface for how tokens are going to arrive, so you can dictate when they arrive, how many arrive for each arrival event. So the schedule source is characterized mainly by this table, and this table gives you a timestamp where you can say that you want tokens to arrive at this time, and it also gives you a quantity column, so you can say how many tokens have to arrive at that time. So the time that you put in the time column represents a number of model time units. So like, for example, if I were to say that this model was constructed in seconds, then at 5 seconds into the start of the model, you would have created 3 tokens. And then at 10 seconds into the model, you will create 4 tokens. And then 25 seconds into the model, you will create 1 token. So this table interface is just saying that you're defining a row for different arrival events that are going to happen in your model. So rather than saying that tokens just arrive like randomly, like we've been doing for the most part, you might want to set up some kind of a schedule that says at this time things arrive, and at this time things arrive, and at this time things arrive. And it's also nice because it gives you these additional controls about how many tokens arrive during each event. So like at time 5, you can say 3 tokens, like I said. Now this arrival table can also be set to be a repeating schedule. Which means that you would say, if this schedule was repeated, where we said at time 5, time 10, time 25, after time 25 executes in the model, we create the tokens associated with time 25, then you would go back to the first row and you would create tokens 5 seconds after the time given in the last row. So if your last row says that you're going to create tokens at time 25, you're going to have another first row of arrivals happen at time 30, because this is the delta from 5 seconds after time 25. And then you would go another 10 seconds after that. So you'd be at time 40 for this second row, the second iteration of the second row. And then you'd be at time 65 for the second iteration of the third row. And then you go back to the first row, which would be time 70, where you create three tokens, and then 80, and then 105, and then so on and so on if you're repeating the schedule. Now, one thing that's also kind of nice about this table-based interface is it does support importing and exporting with Excel. So if you wanted to build a table of arrivals that is going to be applied to the source object, you don't have to set it up in FlexSim if you don't want to. You can set it up in Excel first. You just have to follow this formatting where your 3 columns are time, name, and quantity. Any additional columns that you put into this table will be interpreted as labels that need to be applied to the tokens during these arrival events.
So you couldn't just dump a bunch of data onto this table from Excel. That you still have to maintain the chronological order. Like I couldn't put 10, 5, and 25.
No, you still need to maintain the chronological order. You would need to say 5, 10, 25.
Got it.
So you would need to sort it so that the rows happen in sequence.
So Regan, if you had a 4th column on your Excel document, you said anything else is interpreted as labels.
Yep.
So you could label those tokens that arrive at 5, 10, and 25. Would that make the plus sign at the bottom for assigning labels? Would that just make that redundant?
Potentially it could. So like the difference between having a column in the table to represent labels is that the column gives you potentially some nice flexibility. Where like, let's say that we had a fourth column over here that was type, right? So you have time, name, quantity, and type. What the column value allows you to do is to say that the tokens created on this row maybe are going to be always type 1, and the tokens that are created on this row are always going to be type 2, and the ones on this row maybe are always going to be type 3, right? And so that's nice because that allows you to say that the tokens on this row are assigned label values or assign their values according to whatever scheme you want, and all the tokens in that row could be assigned the same way. The plus sign at the bottom where it says assign labels to the created tokens would be applied to any tokens created by any row.
Okay.
So it's just a slightly different way of differentiating the values that give you some different options. And so we provide for both.
All right. Thank you.
Yep. But yeah, usually if you're using the column-based label assignment, you're probably not going to use the plus sign, and vice versa. Okay, so just wanted to give you a brief overview of this one because it's going to come up handy in the exercise that we're about to build. Oh, and there's actually one other thing that I forgot to mention that's pretty nice about this quantity field. The quantity column, like in here, I have just, integer values. Like at row 5, it's always, or for row 1, it's always going to create 3 tokens. Row 2 is always going to create 4 tokens. But you'll notice that on like row 3, I have clicked on the cell. That's why it's bolded in black. And that means that arrival 3, which is row 3, you have the ability to assign expressions for dictating the quantity of those tokens. So kind of a cool thing here where you could say that, yeah, time 5 is going to create 3, time 10 is going to create 4, but time 25 is actually going to create a random number of tokens between 1 and 10. So that's potentially useful because maybe you have these 3 different arrival rows that you know that the time of the arrival are these times, but the number of tokens maybe is still maybe got some randomness associated with it. So you can highlight the quantity field and input some randomness associated with that. Okay, so I want to give you guys an exercise to build that incorporates all these ideas we've been talking about: the process flow list, the schedule source. And with this model, I want you to think a little bit about how the time unit that you choose for this model might affect the way you do this model, right? Because there's a lot of different ways that time is being used as a factor in this model, using a lot of different kinds of time units. And so it might be useful to think about, well, what's going to be the right time unit to use, right? Should I use seconds, minutes, hours, based on some of the ways time is described here? And I'm going to leave that as an open question for you guys to decide what the right time unit's going to be. Now, the main part of this model, the hardest part of it is usually the arrival rate, the way that we're going to cause tokens to arrive. Now, the other thing that's kind of interesting about this model is that we aren't describing the arrival rate for just one kind of thing. We're actually going to be describing 2 arrival rates for 2 different sets of tokens that represent different ideas in our model. The first arrival rate we need to be concerned with is a shipment of inventory. So what we're going to be modeling here is a simple abstract representation of a warehouse where we have material that arrives every day to be stored, and we have waves of picks that are generated every day that need to be pulled. So our shipment of inventory arrives at the start of every day, and when that inventory arrives, we need to essentially put it away and make it available for our orders. And we also need to generate a wave of picks every day that needs to be created at the start of the day, and that represents the things that we need to pull out of our inventory. Now, both the shipment and the wave of picks are going to be represented by tokens. So you're going to generate one set of tokens that represents the inventory, and you're going to generate a different set of tokens that represents the picks. Now, the arrival time is to have those shipments of inventory and sets of picks to be generated at the start of every day. but the average number of tokens that we receive every day that represent the shipment and the picks in the wave is randomly distributed using the exponential distribution. So that means like on a given day, you might receive 25 tokens that represent inventory, and you might generate 5 tokens that represent picks. But it's just going to be randomly generated. So at the start of every day, when we generate our shipment and we generate our wave of picks, the number of picks in the wave and the number of components in the inventory shipment is going to be randomly distributed using the exponential distribution. Now, this is where I would say that the schedule source can be really helpful, because you can have an arrival row that represents the arrival of that repeats at the start of every day, and then your quantity would be represented using the exponential distribution to represent the number of tokens in the shipment and the number of tokens that represent picks in the wave. Okay, so once you have the tokens being created correctly, we want to assign the inventory tokens a label that tells us the type, and we will distribute those types using D uniform 1 through 5. And so both the tokens in the inventory and the picking tokens will both have a type, and they will both be assigned using D uniform 1, 5. So again, on like one side of the flow, you're going to have inventory tokens that arrive at the start of every day. There's going to be a random number of tokens in the shipment, and there's going to be a random assignment of the type to the tokens that will be between 1 and 5. And then on the other side of the flow, you'll do the same thing for the picking tokens, where they are also generated at the start of every day. The number of picks in the wave will also be randomly determined using the exponential distribution. And then their types will also be randomly assigned using the D uniform distribution. So those first 4 bullet points can all be handled by the schedule source. Just giving you that hint, putting that out there. Now, once again, we've created the tokens the right way, we want to say that the tokens that represent inventory will be pushed onto a list, and we want to use the type of the token as a partition ID. So like if your token is type 2, that represents an inventory component of type 2, it's going to be pushed into the list into partition 2. And then we want our picking tokens to pull one matching inventory token from the list using its type as a partition ID. So again, like we talked about in the previous examples, where the type of the pick, if it's type 2, it is only considering inventory components that are located in partition 2. Okay, now that main part of the description, you can really do all that with really just like 6 activities total. It's a lot simpler in terms of the amount of things that you actually have to do in terms of the number of activities than you may think. The list is doing most of the hard work, and the arrival rate is going to be mostly handled by the schedule source. Now, in the challenge section, we want to allow. I set this up in a way that I want you guys to kind of creatively use everything that we've talked about so far this week, about like managing 3D visuals in a process flow based model with a 3D based model. How could you represent the arrival of inventory and picks as 3D objects? Could you represent the time that it takes to put inventory on shelves using a distribution from 5 to 15 minutes so that those new arrivals don't actually make themselves available to be pulled until after they've been like put away? Can you represent that put away time? Can you represent a picking time using a distribution? Could you also do it using a task sequence? Could you represent the picking operation as a task sequence? Could you represent put away sequence as a task sequence? Can you find the statistics on the list that would allow you to plot the number of unfulfilled orders or back orders every day for an entire year? Could you use the stats of the list to tell you the average number, or rather the average amount of time that an order waits to be satisfied? Can you find the back order stay time? And so, like I said, just focus on doing the description part first. Then if you get that done in a reasonable amount of time, maybe explore some of these challenge options and see some different ways that you might visually represent these ideas in either process flow or in the 3D side. Okay, this will probably take between 30 and 40 minutes to complete for most people. I'll check in on you about 20 minutes in to make sure that you guys are making progress and you're not just stuck. And if you're stuck, then we'll just proceed to the walkthrough, because I don't want this to be the last thing that we go over today, but it may end up being the last thing that we go over today, because there's a lot of things about how this model can tie together everything else that we've talked about this week if you do the challenges. All right, so like I mentioned at the beginning of this problem is deceptively simple with the right activities. So I'm just going to make a new model. And again, the first thing that I mentioned that you might want to think about are things like what kind of time unit would make sense here when we have arrivals that are happening at the start of every day. If we keep the time units in seconds, that means we got to wait some 88,000 seconds before arrivals happen, right? So you might have like an arrival at the very beginning of the model, then you got to wait 88,000 seconds, which is a long time. And so there'd be a lot of like dead time in the model when nothing appears to be happening. So it might make sense to say, well, seconds, probably too short. Minutes, maybe a little bit better. Hours, pretty good. Days, maybe too fast. So I would have chosen probably either minutes or hours to do this particular model. And I'll just choose hours just because. And the distance doesn't matter as much, so I'll just kind of leave it there. And I'm going to start with my process flow. And to kind of help organize things, I would recommend using containers, like we mentioned on Tuesday. And you might say that this container represents the inventory flow. A lot of times when I have a model that uses lists, I like to remember that the job of the list is to help me coordinate between different independent actors in the model. And so that oftentimes means that I have one flow of activities for one of those actors and another flow of activities for the other actor. And the list kind of becomes the way that those flows work together. So this other one I'm going to call my picking flow. Or rather not so much picking flow, but more of like the pick flow. Like how do I know how to generate a pick and how the pick itself flows through its logical process. And the first step for both of these is to handle the arrival rate. And so the schedule source is going to be a good way to handle this, where I'm going to start with a schedule source, and I'm going to say this creates my inventory tokens. And then what is my arrival rate? Well, the arrival needs to happen every day. Now, my model is currently set to hours, which means that for my arrival time, I could say this happens every 24 hours on a repeated schedule. And then in my quantity, I'd have to fill in how often we create, or rather how many of these tokens we create. Now, if you were to type in just the number 10, that means that every 24 hours, we will create exactly 10 tokens that represents inventory. We actually want this value to be exponentially distributed such that 10 is the average. So sometimes we might get 20, sometimes we might get 50, sometimes we might get 5. It just depends on how the random numbers shake themselves out. So instead of just typing in a flat number 10, I'm going to go to the drop-down menu and say that our distribution is going to be using the exponential, and we'll just go ahead and use that scale value of 10. Now, if we just test that to see what it looks like, that means that if I reset and run, that means I have to wait 24 hours before something happens. So right now we're at hour 10, hour 11, 12. There's hour 20. And then at hour 24, we get our set of tokens. And so we let this continue to hour 48, right? We'll get more tokens. So there's hour 48, we get a bunch more tokens, right? Now, with the way it's set up, if we have to run for 24 hours worth of model time before we create our first set of tokens, maybe that's not so bad. But it might also be nice to say that the first arrival happens right as the model begins, right at time 0, and that marks the beginning of the first day. And then we want to create a new set of tokens every 24 hours after that. And we could do that a couple of different ways. The way that I like the best, the way that I think is easiest, is taking advantage of what's called the offset time. The offset time is a one-time evaluation where we offset the start of our arrivals table by some amount of time. So like, for example, if I were to put in 5, my offset time here gets interpreted as 5 hours, which means that my first arrival doesn't happen until time 29, and then it would repeat every 24 hours after that. That's why I mean by it's a one-time evaluation. It's a one-time offset on the first row of the first round of arrivals on a repeated schedule. So by saying 5, that means that it's going to be 5 plus 24, 29 hours. But what's kind of cool is if I put in a negative number here, like negative 24, that means that we're going to offset the first arrival by negative 24 hours, which would put us at time 0, which means that our first arrival would happen at time 0 and then every 24 hours after that. Now, obviously, you probably wouldn't have known to do that. That's why I'm showing it here as part of the walkthrough. I just felt like we were explaining so much stuff that this might have been lost in the shuffle of so many explanations. So since it wasn't required to make the model work, this is a nice bit of convenience to say, oh, I could have offset the time so that even though I'm repeating the schedule every 24 hours, I can offset the first execution of the arrival by 24 hours so that it happens at time 0 and then every time after that. So now when you watch it run, you hit reset. Right at the very start of the model, boom, we're going to get a bunch of tokens. And now we have to wait for time 24 to get the next set of tokens. So there's time 24 right there. There's our new set of tokens. Now we're going to wait until time 48 to get our next set of tokens.
Sorry, I missed what you put in the cell for quantity. You put some kind of code in there?
Actually, all I had to do was click on the quantity field and then go to the drop-down menu down here so that I can use my normal interface stuff. And it just fills in a bunch of code that you don't have to worry about, but it's essentially going to allow this to dictate the quantity instead of a direct number.
Got it. Okay. And you just did an exponential 0 to 10, and that's it.
Yep. Okay, so that gives me the arrival schedule of a new set of arrivals every 24 hours every day, and it also gives me the arrival quantity distributed according to the exponential distribution. Now, the other part of this that is important for the arrival aspect of this is assigning the types. So we wanted to say that the inventory that arrives has a type assigned to it, like a SKU or a part number or something along those lines that indicates what kind of thing it is. And we want that to be assigned using a D-uniform distribution from 1 to 5. Easy way to do that here would be just use the plus sign that allows me to assign labels to the tokens. And I could say something here like my inventory type. And the value would be assigned using D-uniform 1 to 5. And then again, when we get that first set of tokens arriving, we can click on some of these and say, okay, that's inventory type 5, inventory type 4, inventory type 5, type 4, type 4. A lot of type 4s and 5s in here. There's a 3, a 1. So we're getting everything in there. And again, it would be nice if we had some different colors for this. So I'm going to use the change visual approach, because that'll be nice for some things that we're going to do later on. We're going to say change visual, set inventory color. Whoops. And we're going to say this is going to set color by case. The value that tells us what type they are is inventory type. and the object that gets colored is the token. 4, 5. And we will say red for type 1, green for type 2, blue for type 3, yellow for type 4, and orange for type 5. And again, when we reset and run that, now we just see a collection of different color tokens. And if we click on them again, we can notice their different label values. Now, that covers our arrival for the inventory.
Can I
Now
see
we
your,
also, sorry, go
your
ahead.
properties on your source one more time?
Sure.
Okay. Got it. Okay, thanks.
So that covers our arrivals for the inventory. We also need to have the pretty much the exact same arrival style for the picks. And so copy and paste can be our friend here, where I'll just copy these two activities and bring them over here. And I'm just going to change some of the documentation a little bit. So instead of inventory tokens, these are our picking, whoops. These are our picking tokens, same offset, same arrival, same quantity, different label name though. Instead of inventory type, I will call this my pick type, whoops. And using the same distribution. And then on my change visual, we're still setting the token colors, but instead of setting it using the inventory type label, we're going to set it using the pick type label. And we have to do that because the tokens on this side in this container, they don't have the inventory type label. They need to refer to the pick type. And then I'm just going to use the same colors over there. And so now if I hit reset and run, I have two sets of tokens. One set of tokens that represent the picks that my pickers need to go and make in the warehouse, and another set of tokens that represent the available inventory that my pickers can pick. Okay, any questions there so far on the arrivals?
Can I see your properties on your change visual on the inventory actually?
Sure.
I missed that one too. Okay, thanks.
And the picking side is pretty much the same thing. It just references a different label that the pick tokens have. All right, and so now I need to make the inventory available to my picks by putting them on a list. So I'm going to drag out my list. And this is a kind of organization style that I got used to recently, just to try and help refine like the visuals of the story of what my flow is trying to tell, where I'm going to put the list in between these two flows to kind of symbolize the idea that my inventory list is a way to synchronize what's happening between my picking flow and my inventory flow, right? This is going to be like the bridge between these two flows. So on the inventory side, we need to push things to a list. And if you want, you could call this store inventory, because this is what makes inventory available to be made as part of it, to be available to an available order. And if we just leave it at that, right, it just means that when we hit reset and run, all these tokens will be pushed onto the list. And if I look at the list properties, I'll just see that on the entries that I have all of these tokens that are added to the list. And they were all added right at the very beginning. So we had 36 tokens that were added to the list right off the bat. And we can see that we have those entries listed here. Now, one thing that we wanted to do to make it a little bit easier for my picks to find the right inventory to pull is to use their labels as a partition ID. So that means that when I do the push here, instead of just letting them be pushed onto the list generally, I'm going to say that they are going to be pushed and partitioned according to their type. And again, that just means that there's going to be some structure, some organization to this, where if I view my entries now and run the model, I can see all the tokens that belong to partition 1, all the tokens that belong to partition 5, 4, 3, and 2. And those partitions aren't ordered in any way. You'll notice that we go from 1, 5, 4, 3, 2. And that's just because that's the sequence in which the tokens arrive to the push to list. So we created the partitions as we needed them, rather than like knowing ahead of time, oh, we need partitions 1, 2, 3, 4, and 5. Partition 1 was created first, then partition 5 was created, then partition 4, then 3, and then 2, because that just happens to be the order that tokens arrived to this flow, or to this push to list activity. Okay, now I need to do the same thing for my picking tokens. They need to be able to look at this list and see what inventory is available to be picked. So that means I need my pull from list activity. And we'll call this search available inventory. Just make these activities a little bit bigger so they're a little bit easier to read. I'm a little bit OCD about how these things look, so I tend to fuss a lot with like the size of the activities and the names of the activities and stuff like that. But hopefully that makes it a little bit easier to read. And now we will let those tokens go to the pull from list activity. Now in this model, the only thing that we need to do when a puller, when a pick finds a piece of inventory to pull, is to allow that inventory to be released from the list and to tell the puller to stop searching the inventory. And so the only thing that you would really have to do after that would be to have a sync. And maybe this sync on this side represents like ship to customer or something like that. So you can say like ship to customer, because now the component that they ordered has been pulled out of the inventory and it's ready to go to the customer. And maybe you've got a sync over here that represents the end of the picking flow, right? And you might say something just like, this is a sync that represents that the pick is complete. And so that's all you would really have to do to get the main description working. And if we just, rather than run the model, just step through where we see the tokens arrive at time 0, first token goes to change visual, changes its color, gets pushed to the list. So we'll just step through and let all these tokens get pushed onto the list. Notice that the inventory tokens, or that the picking tokens haven't arrived yet, but now they arrive. And now the first token comes through, gets its color set, goes to the list, and it's a type 4. Right? And so when I step, that means that this pick of type 4 is going to be looking for a corresponding inventory token of type 4. So when I step beyond that, I forgot to tell the tokens, the pullers, to look at their partition ID too. My bad. So over here, same thing. These pullers need to be told, hey, look for a partition that's the same as your type. Otherwise, they won't know what to look for. So they become back orders and unable to find things. Let's just hit reset. We'll do that again. So we'll step through, get all the tokens on the list. And then the first token comes through, it's yellow, finds a match with another thing that's yellow. And if we, before the sync destroys them, we can kind of look at it and say, okay, your puller was ID 37. You pulled ID 4. Great. And so that means that they can just be removed from the model now. Next token comes in, it's a green one, finds a green one, they move on. Next one's orange, finds an orange one, and then they move on. Another orange, another yellow. Here's a blue, find a blue, and then move on. Green, find another green, move on. And so on until eventually all of our picks that could find a match have found a match. And what we're going to find is that at the end of the first round of picking, we are left with 17 entries that did not get picked. And at the beginning of the second day, we create 3 more inventory items that get pushed to the list. So now we have 20 entries, no back orders. And now we have to wait for the next round of picking to start at the beginning of the third day. And so we just kind of like let this run fast. Every once in a while, you'll notice that sometimes we have a lot of back orders. Sometimes we have a lot of entries. There's a lot of randomness in this model associated with the quantity of tokens and their type assignments. So it's going to bounce around pretty erratically because we're not doing anything like saying, oh, we should order more inventory of the thing that we have back orders for. We're just saying that we just receive a random set of components from, in shipping. And if they happen to satisfy our back orders, great. And if not, well, I guess we have to wait until the next day's inventory to arrive before we fill those back orders.
Hey, Regan, at
Yeah.
the beginning of the flow, you mentioned that the pick flow didn't have any tokens. So why is that? If the settings were all the same, for why didn't they go in parallel?
Yeah, that's a good question. So let's see that again, right? So again, note the time on the clock, time 0. The first event that takes place is that the source creates a whole bunch of tokens. It is still time 0, right? And then those activities begin to execute. We're still at time 0. And so once we get through all of the tokens here, we're still at time 0. Next event, now we create our picking tokens. And the reason why it happens like that is just because of the order of execution of events, where events that were scheduled to happen at 0 time are being sequenced in the order they're created, because with a discrete event simulation environment, events don't happen at the same time. They may occur in the same clock time, like how all that stuff that just happened all happened at time 0, but it happens sequentially based on the way those events were created. So the tokens on the left got to execute all of their events until their first delay, which is to be pushed onto the list. And then all the tokens on the right got to start being created, starting with their first event, which is to be created by the source. And then as those tokens go through, they cause more events to happen at time 0. So we're just waiting for all those tokens to get through, still in the same time in terms of the clock. But because of the order of execution, they happen in a certain sequence of steps. It's just part of the way discrete event simulation engines work, basically.
Got it. Thank you.
Yeah.
Can I see the properties of your push to list?
Sure.
If that matches. And can I see the properties of your list?
The list itself
It's all
didn't
default?
change. Yeah, it's all the default.
Okay. And then your pull from list?
Is something not working the way that you would expect?
I don't think so. It's kind of, they all get kind of stuck at the list. They never, oh wait, I didn't connect to the sync, so that might do it.
Yeah, that would give you the illusion that pulled tokens were still hanging around because they didn't have anywhere to go.
Yeah, that might have been it.
All right, so I wanted to go through some of the challenges with you here as well, but I don't want to hold you guys over time by a whole bunch. So instead what I'll do is I'm just going to open a model that already has the challenges done. And this is a model that, again, you guys have access to in the training models directory. And if you look at the one that says challenges included, you can kind of see some of the different things that you could maybe do with a model like this, right? Where I just did something really simple here, but this could get even more complex. You can kind of see I did the same thing where I have like my inventory flow and my picking flow. What I decided to do here was to create a task sequence that would allow the boxes to be created first when the tokens are created, and then to allow those boxes, or rather those tokens, to create a task sequence for the boxes to be carried to this item storage area. And then when those things are picked, they go through a picking delay using a delay activity. And when the delay time is over, they would get removed from the item storage to represent that they had been picked. So my picking time is using a distribution that says it takes between 5 and 15 minutes. And you can see those items now beginning to disappear out of that queue. But I could have used a rack for that. I could have created another team of task executors that represented my pickers and actually have them go and take things out of the item storage and maybe even put them on a pallet and put them on a conveyor. It really, once you have like this initial structure where we have a way for the picks to get access to the inventory that they want, we can really start adding in a lot of different activities. You can see that the main skeleton of this model is still here, where we have our source, our change visual, our push to list, and our sync. And we just added additional activities kind of around it, right? And we're using label information here to allow us to do stuff like say, well, if you have a token that creates a flow item, we know that we have a label on it that refers to that item, which means that I can do a load task that says that I want to pick that item up and then I want to unload it somewhere. It allows me to really start to enhance the model with more of the stuff that we learned this week, from creating task sequences, using the objects, and it can grow even beyond this to like some really, really complex stuff if you wanted it to. In fact, let me see if I have like this other version. Yeah, I have this other model that I built that is like the same model, but even more of the same, where now I have a rack and I have a receiving team. That's my put away team. I've got a picking team. And when this model starts running, let me just reset that again. That was too fast still. Time units on this model are hours, I think. So it takes a while you have to run it really slow to actually see the animations because the people are moving in like people time like this. So that looks a little bit nicer. So I've got people that are putting things away on the rack, and I have slots assigned to the rack for the different items so that like all the different, just like what we did with the conveyor model yesterday, where we put things onto the rack where they need to be. And I've got my picking team. You can see I've got my picking team putting things into a pallet, and then they move the pallet to a conveyor that like ships it out, and so again, it's the same sort of stuff that we did, where I've got a task sequence over here to put things away. I've got a task sequence over here to put things on, to collect a batch and put things onto a pallet and then move things to the conveyor. And it's really just all the same stuff that we've been doing, right? But using the list allows the hard part of letting us have pickers that find the right item and being able to use all these other objects with the stuff that we were doing. But it's the same structure initially, where we have our source that generates tokens, we have our push to list activity, and we have our source and our pull from list activity, and then just all this other stuff we do around that. You can see I've got a dispatcher in here that's letting me work with my teams, where I have my put away team dispatcher, my picking team dispatcher. So again, kind of following along with the the model building philosophy that we've talked about a lot this week, where we start with the simplest version of our model first, which is what we did with this model. This is the simplest version of that warehouse where stuff arrives and it needs to be pulled. And then we enhance it by adding in other stuff that we know how to do, like putting things on the racks, using task executors and task sequences, and all that kind of fun stuff.
Question?
Yeah.
Is the dispatcher referenced in process flow?
Yeah, my create task sequence, I'm saying that the task sequence is being created onto the dispatchers. So the task sequence gets created and gets given to the dispatcher, and then the dispatcher gives it to the members of the team.
One other question on your first iteration of your enhanced version. Prior to this one, you had the delay on the inventory side.
Yep.
If you go back to that other previous model for a second.
Yeah.
Yeah, I was looking at that. I was wondering, would it be erroneous, or what would be the ramifications of having that delay after you're pushed over at the pull side? Because that's where I would, by intuitive nature, tend to put it.
Yeah, a lot of times it doesn't really matter.
Okay.
So that's why, like, this version is like, yeah, let's just make the picking time part of, because it's like now the picking time is part of what like the individual box is doing, so it's a little bit easier to access it from over here. In the other picking flow, though, I said that the thing that you pick up is this thing that you pulled off of the list, and so you might instead manage it from over here. It really doesn't matter which way you do it. Because it's just a matter of which way is the data easier to access, right? Because sometimes it might be easier on the left-hand side, because on the left-hand side, we have all the information we need to reference the box. So in order to do that, like where I know what I'm loading, like this pulled box, it's because that the list knows that the thing that we pulled off the list is the box. That was given to me because when the list pulls, it says the thing that you pulled is this thing. In order to make that work, though, when I pushed to the list, I had to say that the thing that got pushed to the list is actually the item that's associated with the token instead of just the token, which is what it would say by default. That's what this push value parameter does. It allows me to say that the token might be at the push list activity, but what's really the thing that's getting pushed? In this case, it's the box in the 3D that's pushed to the list, not the token. And that's what lets me create a task sequence that works with the boxes out here over here, because when I pull from the list, I know what that box is. But if I didn't do that, I would have to have the task sequence part of this flow, because over here is where we have the data available to us about the item. I only have access to that item information over here because I pulled it from the list. Okay, so hopefully this gives you an idea of the sorts of things that are possible. I would invite you to take a look at these models that are available in the download material. If you guys want, I'll put this one on that download site for the videos if you want to be able to pick this one apart too, because it does some pretty neat things. You can see it's got a batch activity in there. We haven't seen the batch in a few days, so it's kind of a neat thing to throw in there. Like I said, hopefully it's giving you an idea of the sorts of places you can take all this stuff, right? Everything that's in this model is something that we've talked about this week. There's nothing in here that is like, wow, you didn't tell us how to do this. This is all stuff that you could potentially do with the tools that we've talked about this week. And that's kind of the neat thing about these tools, right? Is we talked about them in very simple terms, but when you start putting them together into bigger, more complex models, you know, it's the same stuff, but just used in different and interesting ways. And that opens up a lot of doors for the possibility of creating a lot of cool models. Okay, any questions about anything?
I got a question about object libraries or like
Yeah.
operators or the individual items. Is there a resource where there may be more images, or where can I, like, I don't want to reinvent the wheel, and
Sure.
you know, I'm packaging consumer goods, and so if I want to show a machine that packages, I'm sure somebody's have built that before.
Yeah, it's a good question. So one of the nice things about our graphic system is that it plays nice with just about any 3D art file that you can find out there. So whether you do it yourself, like if you have like the ability to like use a program like AC3D or SolidWorks or something like that, you could, make your own essentially art that gets applied to our basic objects. And there are also like online repositories, that are like kind of crowdsourced where people just make cool looking shapes and they upload them. And some of them are actually useful. They're actually like things that you want to use, like stretch wrapper machines and stuff like that. And so you can go to those online repositories. One really good one is called 3D Warehouse, where basically you can download these, I think they're licensed under the general public license. You can just like use them for anything. And you can apply those shapes to FlexSim objects, whether they be flow items or processors or whatever. And they pretty much like those online repositories use the SketchUp file format, and FlexSim works with not the most recent version of SketchUp, but I think like maybe 2 or 3 versions back, just because they update SketchUp, and then if we update our graphics engine to match them, there's usually a few months lag between that. So I'm not quite exactly sure what version of SketchUp we currently support, but that should be documented in the manual if you look under the section that deals with 3D media. And really the manual has really good documentation about how to prep 3D files for use in FlexSim, reducing polygon count and detail so that the shape isn't like too heavy on the graphic system, and what 3D shapes we accept, and like some good practices for using custom media.
Thanks.
Yep.
Obscure question, sir. Have you ever done any cybersecurity representation in FlexSim, or is that out of scope?
That's a good question. I know once a long time ago we built a model that was it was actually a simulation of a web server, where like this was like pre-process flow. It actually would be easier to do these days with process flow, but back then, like we created flow items that represented like HTTP requests, that needed to be satisfied by a server, and like the resources of the server, and how that interacted with all the requests. And so if you can break a system down into a series of events that need to be executed, you can model it. So if you're like interested in, like I said, like cybersecurity kind of stuff, if you were thinking, you wanted to model intercepting and forwarding cyber attacks, using tokens and activities, I think definitely do it. It'd be a pretty creative model, be pretty abstract because it doesn't like look like anything. It's all happening in like ones and zeros, but technically you could do it.
Thank you.
Yep. All right. So like I said, with the remaining time that we have, I'm going to jump ahead past list model 2. This is a very interesting exercise though, where a list can be used to take the place of a combiner. So you would have like flow items being pushed to a list in your 3D view, and then you could set up a process flow token as being your puller. It allows you to do some neat things. So take a look at that maybe on your own time and see if you can get that going. And feel free to email me if you have questions about it. It doesn't really introduce too many new ideas. So with what we've talked about so far, you should be able to get that up and going. But just so that we don't spend time building this model, I'd rather spend the time talking about a couple of new tools, to be used to solve a particular modeling situation where multiple task executors need to be involved in the same task. Okay, so the first thing to talk a little bit about is this idea of what we refer to in FlexSim as a coordinated task sequence. So the easy definition, like I said, is to say that a coordinated task sequence is something that multiple operators need to be engaged in at the same time. So the thing that's challenging about a coordinated task sequence is how you make sure that a task that you give to one operator happens in the right sequence with a task that you give another operator to make sure that they stay like in sync with each other throughout the process. And so that's going to be one of the big things that we're going to talk about in this model. We're also going to take a look at subflow activities as a means of managing repeated logic. And we'll take a look at some examples of using a subflow in a couple of different scenarios so you can kind of get a feel for how they can be used. And so the subflow is actually the first thing that we're going to talk a little bit about. The idea behind a subflow is to accomplish the ability to repeat a block of logic whenever you want to, so you don't have to like remake the logic every single time you want to use it, which allows your logic to get condensed so that you don't have a lot of repeated behavior over and over and over again, but you could just have a subflow that defines the behavior once, and then you can invoke that subflow from anywhere else in your model where you need to cause that same behavior to happen. A subflow is also a nice way to change the control or the flow of logic from a series of like top level processes to a process that is better defined as a series of sub processes. And so like in this little simple diagram, you might have like, you know, some activity happening followed by another activity. And then when you get to this process, maybe it makes more sense to define it as a repeatable multiple executed subflow, where you turn control over to a series of sub processes for the duration of this process. And then when all the sub processes are done, it returns control back to the main process that called it. And then it continues kind of like the top level processes from there. In sort of old school computing terms, you might have heard this sort of behavior referred to as a function or a subroutine, where you temporarily shift the control of logic to a series of sub processes that can be invoked at different times along the flow of logic in a computer system. And so subflow is sort of the FlexSim version of that, where you can temporarily shift control over to a predefined series of steps rather than having to define it in line with the main flow of your logic. Does that make sense so far?
Yep.
So in process flow, to use a subflow, there are three activities primarily that are part of the subflow system. There is the activity called run subflow, first of all, that allows a token that reaches the run subflow to shift control over to any subflow activities that you define. And you mark the beginning of a subflow with a start activity, and then you mark the end of a subflow with a finish activity. So in sort of like a general sense, you might structure things like this, where you have activities that are executed until you reach the subflow, and then the token that arrives at the subflow shifts control over to the start activity, and then any activities between the start and the finish are executed before allowing the token that hit the run subflow to be able to continue flowing on from there. Now, to kind of facilitate this idea of shifting logical control, the run subflow activity creates tokens that are considered children of the calling or the invoking parent token. So there's this idea of parent-child relationships that we can create between tokens, where a token that reaches a run subflow activity becomes a parent for tokens that run through the subflow on behalf of the parent. And so we create this family tree structure between parents and children that we indicate with a number on the parent that tells you how many children that parent has. And then when you click on a token that is a parent token, it draws a red line over to all of its children. And so when a subflow is begun by a parent, really what happens is that the parent creates child tokens that go into the subflow and begin executing all those activities on behalf of the parent. Now, there's some interesting things that happen with this parent-child relationship, especially as it pertains to the sharing of data, like label data. By default, child tokens inherit information from their parents in the form of their labels. So, for example, if this parent token has labels on it, then those labels can be inherited by the child. And then you can set up rules about how that data is allowed to be accessed and used by the child. So you can give a child read-only access to the parent labels so that the child can read the parent labels. You could also give the child token write access to the parent labels so that a child could actually update or alter the labels that are being carried by parents. And you'd have to be careful with that sort of thing sometimes, because if your children have read and write access to parent labels and they update a parent label in a way that you don't anticipate, that could have an adverse effect on the parent. So you do have to be a little bit aware of what happens when this label data is being shared between parents and children, as not to accidentally cause something weird to happen with your parent. That's why we give you like essentially permissions settings on the child tokens, so that you can decide how best to allow child tokens to interact with parent data. Okay, so before we do an example, just to kind of review, the idea behind starting a subflow is that you have in an event where the subflow takes over. That's going to be the run subflow activity in process flow. And then you have a start activity where the child tokens are sent in order to perform actions on behalf of the parent. And while the children are flowing through the subflow, the parent token waits for all of the children to finish what they're doing before we allow the parent to continue off of the run subflow. And then the finish activity marks when control is given back over to the parent. And when all the children execute the finish activity, then the parent token can continue its flow away from run subflow. All right, so let's take a look at a simple sort of example of that, and then we'll look at a larger example. So I'm going to just open a model, just do a new model. And in my process flow, I'm going to have a source that I'll send to a delay, just sort of setting up some parent processes. And then I'm going to say that a subflow is encountered after that second delay. Now, again, notice that the run subflow activity has that exclamation point on it. But in this case, rather than indicating that the subflow wants to connect to a shared asset, the run subflow activity needs to have a destination to send children to. And so that means I need to bring out a start activity and connect the run subflow with the start activity so that we can send our children over to the start. Now, this is going to be a pretty simple subflow. I'm just going to do a couple of delays. But remember that any activity in the library can be part of a subflow set of activities for a child. But I'm just using delays to kind of keep it simple. And then when the subflow is over, I have my finish activity. And then I'm going to have another delay for my parent, maybe another couple of delays, and then a sync. So if we, and actually, instead of using this source, I'm going to use a schedule source so that we can just see one token do this at a time. So I'm just going to use a schedule source that creates one token at the very beginning of the model, and then that's it. This is not going to repeat I just want to create one token and that's all. Because it's a little bit easier to keep track of what's going on if you see it that way. Now, one other thing that I tend to do with a lot of the subflows that I use as far as formatting is sometimes I'll do stuff like this, where you have the run subflow activity and then the activities are sort of like indented in the block a little bit. You don't have to do that, but it just kind of helps me understand that the subflow is here and then the run subflow executes as sort of like in this general sort of an area before we move on to this delay. But it's just formatting, kind of like how I do with the list. Doesn't change anything. The important thing is that you have the run subflow, the start, and the finish. And so if we watch our token come through, our token is just happily going along, just like our normal tokens do. And then when it reaches the run subflow activity, you're going to see that that token becomes apparent. And so I'm going to slow the model down, and we can see now that this token is apparent because it has that number 1 in it that says I have one child, and I follow the red line to say that my child is located over here. And if you click on the child, you get a teal line that points back to the parent. And so the parent token is just waiting at the run subflow activity, waiting for the child to do all of the activities that are part of the subflow. And then when the child finally finishes those activities, then control is given back to the parent, and the parent can move on off the run subflow and continue on in its flow as normal. And you can see that the red number that tells you how many children the token has is now gone, because this token has is basically all of its children are now removed from the model because they did their finish activity, they turned control back over to the parent, and they no longer exist.
I do have a couple of questions, but I think you're gonna mention that afterwards. But subflows have can I put capacity on the subflows? Like I have several the run subflow item related to the same subflow. Is there a way that I can limit myself? Can I attach resources in a way that it limits? Like I have several activities which is loading trucks, right? But I only have one loader, let's say. So can I use the subflow and attach to a resource, and the other ones would be waiting? Is that it?
Yeah, for sure. Yeah, you could so if I had instead of just creating one token, I'll go back to an inter-arrival source so that we create lots of parents. I could say that there is a resource that needs to be acquired as part of my subflow. And so when my parents then send their children into the subflow, right? That parent has its child currently using the resource, but subsequent parents would send their children into the subflow, and they now become requests on the resource because the resource that the children need to do whatever this block of activities means is no longer available. And so you start to get queuing as multiple parents send their children into the subflow, and they need to acquire a resource or enter a zone, maybe pull from a list, any sort of shared asset that you want to use, like that you would use normally in a model, you can also use as part of the subflow, where the child is actually using the resource on behalf of the parent, which is causing other children to have to wait for that resource to become available.
Right. And I can have more than one flow linked to the same subflow, right?
Yep, absolutely. Yeah, that's one of the really nice things about the subflows is that you can define this block of activities once. And so if I have another block of activities over here that maybe says that we create a token and then it just goes directly into the subflow, I can say that you send your children over to this start activity as well. So I can define this block of activities once and then invoke it from multiple points using the run subflow activity.
Okay. And if I want to prioritize which flow gets to do the subflow first, should I create like a list and see?
Yeah,
and see
either a list or a zone. So the thing to do would be to have labels on the tokens that originate from the various flows, and a zone would be an easy way to prioritize entry like into the main activities of a subflow, because a zone has a queue strategy that you can use that says how the tokens are allowed to enter a zone. That's kind of an advanced feature of the zone that we didn't talk about yesterday. But if you look at a zone and go to the properties under advanced, there is a queue strategy that you can use to say that tokens that are trying to enter the zone are accepted into the zone according to basically an order by query that you can set up.
Okay. It's order by token dot type.
You wouldn't need the token. You would just say order by type.
Order by type. Okay.
Yeah, because the zone would understand that we are
referring to the token.
We're querying tokens that are trying to access the zone, so it doesn't need to be explicitly told that.
Okay.
And again, that's kind of where like the zone and the list have some overlap, right? Because the queue strategy of the zone is a lot like the query of the list.
Yeah, but it's simpler, right? In this case.
Yeah, because with the zone, you don't need that other entity executing the query. It's just built into the queue strategy of the zone. It's basically like the zone is pulling tokens off of like an invisible list to allow them to come into the zone according to the queue strategy that you set up.
Right. Yep.
Okay, so to kind of see like another way to kind of see like a full version of how something like this might get used, I'm going to open our process flow model from Tuesday. And again, you guys have a copy of this, so you can see this exact same thing being done in an actual model. So remember, we had our different phases, right? And so if we take a look at the 3D object model that we did, and then in my process flow, I have a version of my flow of activities that uses a subflow. Hang on just 1 second. I need to make sure that other things are not going to interfere with what I'm doing here. So here's a version of our model using a subflow in place of recreating the same block of logic in multiple places. So remember, in our 3D challenge version of this model that used like our simple approach with just like create, move, and destroy, I had to recreate the exact same block of activities multiple times. And the only difference between these blocks of activities was what resource was being acquired. But I can use a subflow to condense this a little bit so that I can say that there is a label that's being assigned that tells me what resource I want to acquire. And then I can run a subflow into a block of activities that has my acquire, my move, my delay, and my release, all as part of a subflow, and invoking that subflow from various points along the different flows for the different phases that I designed. So when you run this version of it, the parent tokens send their children into the subflow to acquire the right resource and get moved to the right location, while the parents stay in the main part of the flow. The children are executing the subflows on their behalf.
How do you choose the right resource?
By using a label. So I have a label that says that the resource ID that is assigned in this block is resource ID 1, resource ID 2. And then when I come to my acquire, rather than explicitly acquiring the same resource, I'm using an option that says that I want to acquire a resource by case. So this is on the acquire activity that says, based on what the resource ID label says, if it's a 1, acquire inspection. If it's a 2, acquire painting. So all my shared assets are down here in this little container with my subflow. And when the tokens arrive to the acquire, they know that they inherited information from their parent about what type of thing they are, what item they correspond with, and what resource ID they need to acquire.
Great. And the resource ID is not like an output port from the acquire, right? This is from the model.
Yeah, I assigned it as part of the assign labels activity. So I created like this legend that said that when I use my resource ID label, these values correspond with these resources that I want to acquire. So like if you look over at the painting block over here, it says that the resource ID is 2, so that when the parent sends its child into the subflow, the child knows to acquire the resource based on this case definition that says that resource ID 2 means I need to acquire painting.
Can you click on the painting?
Sure. Whoops.
Then in each process you are writing the label, right? Because you assign first.
Say that again. You sound like you're underwater.
Oh, sorry. You say that I'm saying that you are rewriting the label.
Yes.
In each process.
Yeah. Yeah, I'm assigning the label myself to say that, okay, if my token ends up here, then I know that means that we're in the inspection block. So then when it's time to acquire a resource, you should acquire the inspection resource if you came from this block, or this block.
Right.
So if you instead of putting case by number 1, 2, 3, 4 and do the link with what you said, could I put like assign labels and put like a text saying resource inspection, and that will be the same? Because I'm trying to understand how does it acquire finds the resource inspection. It's only yeah.
So I did it the resource by case just because I'm used to doing things like this, where I assign a numeric ID that correspond with a resource. But you could also use the option here that says resource named. And so in here, you could put in a label. Like if I had a label that was like the resource ID, if instead of being a number, it was the name of the resource, exactly as the name of the resource appears here, then you could do this instead.
Okay.
But that would mean that I'd have to name that my resource, or that my label value would have to be a text value instead of a numeric value.
Okay. In my case, I have like 30 resources differently. The best way to do is doing like a global table, 1, 2, 3 by 4, and linked the name of the resources. Is that it? How
yeah, you can do that. Yeah, if you set up a global table where the name of the resources was in, well, you might name me, well, yeah, I mean, you could do it that way. And like say for each row, you know, for a given row in the table, get the name of the resource and apply that to a label on the token. And then you could use this resource named thing to do that. Now, the only reason why I shy away from doing things by names like that is because if you make one spelling mistake, it all falls apart.
Yeah. But in this case, you have the same problem, right? Because when you do the by case, you see the 1, but you have to write down in the case.
Now, because with the by case version allows me to use the eyedropper and say put in that name.
Okay.
So like for any case that I add, I can just say, you know, get the name of that resource and just use the eyedropper to get it. It knows how to do that. But with a global table and label names, it can be a little bit more dicey.
Okay, got it.
So whenever I can, I like to turn stuff like that into numeric IDs and numeric identifiers, just because I trust numbers a little bit more than I trust my ability to type.
Yeah, I understand. Me too. Okay, got it. Yeah.
So in this example, then I used the subflow to make it so I didn't have to recreate the same acquire, move, delay, or release every time, because they're all the same except for what resource they needed to acquire. And so it's like passing an argument into a function by having this label value that says, hey, the resource that you want to get is the first resource or the inspection resource. And my children know how to do that based on what the acquire says by getting a resource by case. And so that information is sent into the subflow by the parent so that the children can make decisions about what to do in the subflow, which is kind of cool. And that also allows me to retain the structure of my logic so that it still looks like a nice, clean, well-organized flow chart. But I have like the subflow down here that's really doing the important work, but I don't have to look at it. I can just look at what's going on at the parent level instead of worrying about what's going on at the child level. Right? Does that make sense?
Yep.
Yep.
Okay. Now, in process flow, we use subflows quite a bit for this sort of thing, but we can also start subflows from the object environment as well. And the same rules kind of apply, where in order to start a subflow from the objects, you need to have an event that marks where the subflow takes over. You need a start activity that can receive your child token. And then you have a finish activity that says when control is given back over to the parent. And so a really common subflow that comes up in the object environment quite a bit is using transport, where if you wanted to basically define a customized task sequence as part of the use transport event of an object, maybe you like everything else that the object does, and you just want to replace the built-in task sequence with your own task sequence, you could use a subflow to create a custom task sequence for you that the object can invoke when it's time to use transport. So just give you kind of like a simple version of that. So say that we've got our source, we've got our queue, we've got a processor over here, and then we've got a sync and an operator. So I'm just going to connect these together as normal, including a center port connection for the operator. And so if we come over to the queue, right, and just say use transport, then that's going to create a task sequence for us that will allow the operator to travel to the queue, pick up the flow item, carry it to the processor. But what if there was like an intermediary step that I wanted the operator to do? Maybe I've got like this shape object that I'm going to call a scale. And when an operator picks up a flow item from the queue, he actually needs to bring it to the scale for a short delay before being able to continue on to the processor. Well, with what we know how to do right now, that would actually be fairly complex by creating a customized task sequence and using event listening to kind of kick it off. And I wouldn't be able to take advantage of things like send to port. Like, for example, if I had a second processor here and I said that I just want to send to a round robin processor, but before you go to the processor, you have to visit the scale first, it becomes much more complex, basically, with what we know how to do so far. And so by creating a subflow, I can take advantage of all of the things that the queue knows how to do and only turn over control the process flow to execute the transport of the flow item without having to do things like event listening and figuring out where the flow item is going to go. I can use the port connections of the queue to arrange that for me. And so if I want to take advantage of a subflow to define my own task sequence, if I go to the process flow button, rather than creating a general subflow, you can create a subflow instead. And so this is a special process flow window that knows how to work together with subflows that are invoked from the object side of the model. So I'm going to say that I want to add a subflow, and in here I'm going to just put in a start activity. And then on my queue, rather than saying that my transporter is whoever's connected to my center port, I'm going to say that I want to design a customized piece of logic that starts a subflow process flow. And that's going to give me this window that says that we will send a child token into this subflow, which is this window, into a start activity, which is this start activity. And then these labels will be assigned to the child token so that I can build a task sequence that allows me to transport the flow item. So this information will all get passed into the subflow in the form of token labels. Like I'll get to know the item that needs to be transported. I get to know the port connection that was selected during the send to port event. I get to know the from object or the origin of the flow item. And I get to know the to object or the object that's connected to the port connection where we want to send the flow item. And then we also get to know a dispatcher, which is whoever is connected to my center port connection of the queue. And so all this information will be assigned as a token to, as labels on my token. So if we just kind of watch what we have here, when I hit reset and run, when a flow item wants to be sent to a processor, I now have a token in the start activity. And the information on the token tells me that the item that's in the queue wants to be transported. It was sent to port number 1. The from object is Q1. And the to object is processor 1. And the dispatcher is operator 2. And so that creates the token, and now I can build my task sequence. So like I can say that I want to create a task sequence. And my task sequence will be created onto my operator. And I can get that from the label that's on the token. I can just say token.dispatcher. Because remember on the queue, the label dispatcher passes in whoever's connected to my center port. And so the task sequence will be created onto my operator because that's who the dispatcher is. And then I can say that I want you to travel. And now who am I going to travel to? I'm going to travel to the queue, which is given to me as the from object in the token labels. And then I can say that I want to load the item from its container. And then I'm going to, if I put in a travel here and say that I want you to travel to the to object and then unload the item to the to object, and then finish that task sequence, and then also finish the subflow. Oops. So basically, this recreates the standard task sequence. If I were to just to run this, then I'll see a token in the subflow that tells the operator to do all of the standard operations that the queue would normally tell it to do. This is going to behave exactly like the standard task sequence, right? And notice that all I have to have in here is the task sequence. I don't have to have an event-triggered source because the token will be created into the start activity for me by the queue. I don't need to worry about checking to see if the processors are available because the port connections between the queue and the processors are doing that for me already. I don't need to do any waiting for an event because, again, that's all being handled by the standard object behavior. I'm just controlling the part where the flow item is transported by the operator. And so this is just a recreation of the standard task sequence. Now, from here, I can start to add customized actions. Like, for example, instead of traveling to the from object, potentially, I could say instead, I want you to travel to the scale. And then I want you to delay while you're there for maybe some triangular amount of time. And then you can continue traveling the rest of the way. So now when a flow item gets picked up at the queue, we bring it to that scale object that we created, we delay for a while, and then we carry it to the to object. Because I was able to add in my own customized steps as part of my task sequence. All right, any questions there so far?
Nope.
All right, now, so because this is also a subflow, that means that if I copy all these objects, and this Q16 is using the same subflow, that means it will send child tokens into the subflow as well. Because now I have a reusable block of code that controls the operators that can be invoked from any other object in the model that I want.
And then in the case that you are using scale, you can assign as a.
Sorry, you sound really, really far away.
Oh, sorry. Okay. In the case that you are using the same scale, and you have just one resource, you can assign as a resource there just to use one, and the other was just wait.
Yeah, in this example, they're using the same scale object, but if I, like for example, let's say that they have their own scales, right? So I could make a center port connection to the scale, and then on the queues, I could say let's add another label to the token, and say this is the scale, and this is going to be center object 2. I'll do the same thing from Q16. I'll say we're going to add a label to my child token. That is the scale. And that is going to be center object 2. And then when it's time to travel to the scale, rather than going explicitly to the scale, I can say go to token.scale. So now operator 16 will go to his scale, and operator 2 will go to his scale, because I said that the destination now is found on the token by looking at the scale label.
Sorry, I had to step away for a moment at the beginning. The travel and load and all those things surrounding going to the scale, those were default values, and the labels that are generated by the queue for those values are default as well when you choose this transport task sequence.
I had to add the scale as a label to the token myself.
Yeah, but the other ones like
but the other ones are all
destination
there.
And all that.
Yeah.
Okay, cool.
Yeah, the other ones like item port, from, to, and dispatcher, those are always going to be the default labels. I just had to add my own additional label.
Cool.
And that's kind of nice too, because you can add whatever labels maybe that you might need, right? If there's other information that the subflow needs to know about in order to execute this kind of a task sequence, you can pass any of that information into the subflow as a label. And again, the nice thing about it, you define it once and you invoke it from whatever objects need to do this kind of behavior. It makes for really easy reproducibility without having to recreate the same steps of logic over and over and over again. And then you just use labels to handle the slight variations that may exist between different implementations of the same block, like what resource to use, or like in this case, what scale you want to send your operator to.
Nice.
Okay, so why don't we go ahead and take a 15-minute break. And when we come back, we'll talk about another set of activities in the process flow that allow us to do token coordination, the split, the join, and the synchronize.
Oh, Regan, I'll have a meeting in 20 minutes that's probably gonna last between 30 and 45 minutes. So I'll probably be away after that break.
Okay.
Just out of curiosity, what are we gonna learn afterwards?
The split, join, and synchronize activities. We're going to go over those, and then I'm going to give you guys a model to build.
Okay, and then
that'll be it.
That'll be it. Okay, so will you think that it's gonna last more than 30, 40 minutes, or
the model building exercise?
yeah, this whole after break?
It usually takes about a half an hour to 40 minutes. And then like the walkthrough that I do takes about 20 minutes.
Okay, so I will try to jump in right well, as soon as I can. So
okay.
That sounds okay. Thanks.
All right. And for everyone else, I'll just see you back here in 15 minutes.
All right.
All right, you guys ready to start up again?
Yep.
Okay. So just really quickly going to go through a couple of activities that you might find useful for a lot of things, but also for the model example that we're going to build. And these are the coordination activities. And so in the process flow library, you'll find a set of activities that allow you to split tokens, join tokens, and synchronize tokens. So the first one that we'll talk about is the split. So the split activity wants to receive a token, and then it will make additional tokens equal to the number of outbound connectors from the split. And with the split activity, you have the option to assign these newly created tokens as children of the original token, or as independent tokens, or as siblings. So they can be treated as though they have the same parent as the original token. Independent token is the default because that tends to be what people want to do with the split activity. But if you want to take advantage of any of the parent-child stuff that we talked about, like how like label data is shared and things like that, then you can do that from the split activity as well. So if you take a look at the way split is used, I'm just going to make another new model. And have a process flow. And so if we have a token that is created by a source activity and send it to a split, the split activity needs to have outbound connections. So I'm going to start with just 2 outbound connections. I'll just have it connect to a couple of delays. and then have another delay here. And so if you just sort of step through this, there's our first token. It comes to the split, and then one token goes into the split and two tokens come out because that's how many outbound connections we have. Now, the connector numbering is pretty important, where the first outbound connection is reserved for the original token. So again, when the token initially comes to the split, this token has a unique identifier. This is token ID 1. And then that token ID 1 is actually the token that goes out of the outbound connection number 1. So again, if you kind of click on the token and follow it, the original token goes to the delay connected to outbound connection 1, and the newly created token goes through outbound connection number 2. Now you'll also notice that if you take a look at these two tokens, tokens ID 1 and 2, there is a label on them called split ID, and that is assigned by the split activity, where it says assign a split ID to token.splitID. Now, this split ID label allows the tokens that come out of the split to know who they came out of the split with. So the original token, ID 1, becomes the identifier for the split ID. And so ID 1 belongs to split ID 1, and token ID 2 also belongs to ID 1, so that you know that both of these tokens were part of like the same original token. They were both created from the same original token. And if we were to add a third outbound connection, that just goes into like another delay. When I reset this, one token again goes into the split, and now 3 tokens come out, and they all belong to the same split ID. They all originated with token ID 1. So this is token ID 3. It's part of split ID 1. Token ID 2 is also part of split ID 1, and token ID 1 is also part of ID 1. So all 3 of these tokens originated from the same token, which is ID 1. Right, so far so good. Now, because all of these tokens come out of the split and come to other delays, that means that I can have them begin executing whatever activities I want them to do. So I'll just throw in a couple of delays here. And if you hit reset and run this, you'll see that the tokens are just all executing their own delay times in parallel with each other. So the tokens are created, they're sent to their activities, and they just start executing activities one by one, just as if they come out of a source activity themselves. But the split activity means that additional tokens are created from one original, and then they just start executing whatever activities they need to execute after the split. Now, the join activity is used to allow tokens that maybe had been split off from each other in the past to be rejoined with each other again later. So the join activity knows how many tokens it wants to join based on the number of inbound connections that the join has. So again, the number of the connectors really matters to the split, the join, and synchronize. The split activity knows how many tokens to make based on how many outbound connections there are, and the join activity knows how many tokens to join based on how many inbound connections there are. So if we draw a connector from this block into the join, that tells the join that it needs to receive 1 token through this connector. And then if I make another connector from this block, that tells the join that I need to receive 1 token from that connector. And so those tokens will be joined together into 1 token. And again, it just assumes that it receives 1 token from each connection, And once it receives one token from each connection, it considers the join complete. So I'll just throw another delay after the join there. And this is just a bit of formatting that I found myself using a lot with split and join and synchronize, is I use the join and make it longer if I have activities that are like feeding into it like this, so I keep track of the connectors a little bit better. And so if we let this run, then the tokens will begin executing their delays. And when the first token arrives to the join, you can see that it makes a progress bar. And so now it tells us that we are 1 out of 2 on joining 2 tokens from split ID 1, because by default, the join activity wants to rejoin tokens according to their split ID. That's what this little expression here means. If the tokens that go to the join don't have a split ID, then you can join any tokens together. But if they have a split ID, then they want to be rejoined with things that have the same split ID as themselves. Now, once both tokens arrive, we just reset that and do it again. So we're going to see the first token arrive, and that tells us that we're 1 out of 2 on the split ID. And when the second token arrives, those 2 tokens will be merged back together. So the result of the join is 1 token, and you'll see that it's actually token ID 1. The original token, or the token that arrives to the join on inbound connection 1, is the token that represents the merged token. So you can see this is token ID 1, it's still part of split ID 1, but now the other token, token ID 2, no longer exists because it was joined, quote unquote, with token ID 1.
So if there are multiple tokens going through the process flow, will this join activity know to take 1 token from the left and 1 token from right, instead of taking 2 from, you know, the right one?
Yeah, that's just the way the join is designed. The join assumes that for as many inbound connections as it has, that's how many tokens it requires to be joined. And it also assumes that it has to receive 1 from the first inbound connection and 1 from the second inbound connection. So it'll never join 2 tokens from the first inbound connection. It just will never do that. It always joins 2 things from each connection, or 1 thing.
Even the split ID is the same. So they'll take 1 from connection 1 and 1 from connection 2, right?
Right. So like if we change out our single source for a source that's creating lots of tokens, right?
Mm-hmm.
We're going to see that some tokens from different split IDs will arrive first. So like here's 1 out of 2 for split ID 5. Here's 1 out of 2 for ID 8. Mm-hmm. And 1 out of 2 for IDs 14 and 11. So we've received 4 tokens into the join, but because we have a split ID label on them, it is assuming that we want to only join similar split IDs together. And so we don't know where all these tokens came from. We don't know if they came from inbound connection 1 or 2. But what we do know is that eventually when a join does take place, like this is token ID 14, that we are going to get 1 token from each of the inbound connections. And it's by default segregated by their split ID. Now you don't have to rejoin based on their split ID. You could rejoin based on a type label. You could rejoin based on any label at all, or by no label. If you were just to delete this, right, then that would mean that you can join any 2 tokens from the 2 connectors in any order. It's not going to wait for the other thing that belongs to the same split ID if you just X out the partition ID. If you X out that field, then that means any 2 tokens from the 2 inbound connections can be joined together. Or you can use any other label as your join, your join parameter. but the default is to use token dot split ID. And the question mark means that if the label doesn't have a split ID, then it'll be put into a partition for joining any tokens together at all. So you don't have to have a split ID to come to the join. If you don't have a split ID, then we can still join you with something else, but it would have to be something that also does not have a split ID.
Is this rule applied to the partition ID in the pool?
No. No, this is just how it's handled on the join.
Gotcha.
Okay. Now, what about that that third token that we had that was off in the other delay, right? When we get to this point where we have these two tokens that get joined back into one, and then we have still this other token out here. Now, we don't necessarily have to rejoin it with anything. It could still be an independent token off doing its own thing if we needed it to. But we'll use this third token to illustrate how to use a synchronize and see how it's similar to a join, but also very, very different. So if we bring in a synchronize activity, remember that one token comes out of the join, so we can send one token into the synchronize, and then we'll send another token into the synchronize from the third delay. And again, when you click on the synchronize, note the connection numbers. Inbound connection number 1 means that that is ostensibly for the original token. Whenever you're keeping the original token that you split off from, you should always make sure that the original token travels to other activities through the first inbound connection to the next activity. So like on the join, the first inbound, I reserved that for the original token, and for the first token into the synchronize, I also reserved that for the original token. Now we have inbound connections 1 and 2, and so like the join, the synchronize knows that it needs to receive one token from each of its inbound connections in order for the synchronize to happen. So because I have 2 inbound connections, it wants to receive one connection from the first inbound and one token from the second inbound. Okay, now what's different about the synchronize and the join is what comes out of the synchronize. So if I have a delay activity, the synchronize requires that for however many inbound connections the synchronize has, it has to have the same number of outbound connections. So the synchronize allows me to have multiple outbound connections, because if you have 2 inbounds to the synchronize, you must have 2 outbounds from the synchronize. So the reason why you have to have those 2 outbounds is because when the synchronize receives the tokens that it wants to synchronize, it releases those tokens through the same numbered outbound connections as its inbound connections. So we just received one token into the synchronize. This came from inbound 2. So the token that is in the synchronize right now is waiting for something else of the same split ID to arrive to the synchronize. And when that other token does arrive, 2 tokens leave the synchronize through each of the outbound connections. So when you synchronize tokens, they aren't merged together. One isn't destroyed. You get both tokens, but they have to travel out of the synchronize through an outbound connector that is the same number as the inbound connector that they arrived on. So if a token arrives to the synchronize on inbound 2, it will always leave the synchronize on outbound 2. And for the same reason, something that arrives to the synchronize on inbound 1 will always leave on outbound 1. So you can have them connect into the same activity like I did here. And you can see that here we have token ID 3, which arrived on the second inbound connection. It's part of split ID1. And then you also have token ID1 that arrived on inbound connection 1 and left on outbound connection 1 and is also part of split ID1. And so if you didn't want them to go to the same activity, that's fine. You could do 2 delays. You could say that you've got a delay here or any other activity, right? I'm just using delays as an example. And so if the first outbound connection goes into this delay and the second outbound connection goes to this delay, then when those tokens are synchronized, they're again sent out from the synchronize to whatever activities you want them to execute from then on. So again, we're about to get our second token into the join so that we get 1 token coming out of the join. And then the 2 tokens go into the synchronize, and then they're released by the synchronize to whatever activities are on the outbound connections that are the same number as their inbound connections. All right, any questions about the split, join, and synchronize? Okay. So going to give you guys a model exercise to do then that kind of ties together everything we've talked about with regards to subflows being invoked from the object environment and using the split, join, and synchronize activities to help us build a coordinated task sequence. So the model layout that you're going to build looks like this, where you're going to have a source that feeds into a queue, and then you've got 2 outbound connections to downstream queues, and then processors, and then a sink. Then we're going to have 2 operators. And we're going to say that the flow items arrive every 20 seconds into a queue, and 2 operators are required to carry it to a round robin downstream queue. So the idea that we want to simulate here is that the flow item can't be transported by 1 task executor alone. It needs to have both task executors involved in carrying the flow item to the downstream location. So like maybe you think of the flow item as something being so heavy that it takes 2 people to carry it. Or like you have like a chain of custody rule where 1 person carries the flow item and the other person is like an escort. And so the idea, again, is that flow items come into the queue and both operators are required to be involved in the transportation of the flow item such that it looks like they're both carrying the flow item at the same time. Now, because of the way like the load activities and things like that work, you can't really have both task executors physically holding the same flow item at the same time. 1 person is going to have to carry it, and the other person needs to stay in sync with the other operator so that it gives the impression, or it looks like they are both working together on carrying the flow item. Okay. We're also going to say that the task executors have a load and an unload time that's defined by the triangular distribution. So on an operator, you're going to go to the object properties, and you're going to find the load and the unload time. And you're going to say that the load and unload time is given by the triangular distribution with the parameters that we say here, where it takes at least 2 seconds, at most 8 seconds, but usually 5 seconds to load and unload the flow items. And so the easiest way to accomplish this is with a subflow process flow that will be invoked from the use transport of the queue, of the upstream queue. And so you'll create a token into that subflow, And then you'll design a task sequence that allows the two operators to coordinate with each other as they carry the flow items to the downstream destination. So keep in mind what we talked about with the token that gets created from the use transport subflow task sequence, where we have all of this label data that gets passed into the subflow that we can take advantage of in order to build the task sequence and have the operator carry, or have the two operators work together to carry the flow item downstream. Now, my recommendation would be to build the 3D model first, of course, and then build a custom task sequence that mimics the standard behavior where only one operator carries the flow item to the queues. And then think about how you'll use things like split and synchronize in particular to allow a second operator to be involved in the transportation of that flow item so that it looks like they're working together on the transport. Okay, so this is a kind of a funny example because it sounds really simple. It's a scenario that's really easy to describe in human terms, to say two operators work together to carry the flow item, no problem. But to actually design the activities to cause that to happen takes a little bit of doing. You'll need to think about what happens every step of the way when both operators need to look like they're walking together and look like that they're standing next to each other while one is physically loading the flow item and unloading the flow item, to make it look like they're working together throughout the entire process so that they're both properly accounted for in their movements and in their utilization as they work together on this process. All right, any questions about the description? All right, I'll give you guys a few minutes to work on that. Like I said to Tiago when he asked about it, this will take probably about 25 to 30 minutes to figure out and do. And then we'll do a walkthrough together so I can describe, the steps that you would take. And really think about building this step by step. Try a little bit of things out, test it to make sure it behaves the way that you think, and then add a little bit more, test it, verify it, add a little bit more, test it, verify it. Don't try and do it all at once because you're more likely to make mistakes that way, so that you can kind of see the evolution of the process from something very simple up to something a little bit more complex. Okay?
Great.
All right, good luck. Let me know if you have any trouble or if you have any questions, and then we'll do a walkthrough together.
Hey, Reagan.
Yeah.
So I think I have it. So I think I have it done besides the challenge. I was just having a question. So one of my operators stops right at the queue where it's supposed to be delivered, and the other one kind of walks into it. Mm-hmm. Is that how it's supposed to be, how this model is supposed to turn out, or are they both supposed to walk the exact same distance?
Yeah, with the reason for that extra little, because like they both get to the queue, right? And one of them takes like a 2-step in, basically, right?
Yeah, to put it in its exact spot.
Right. That's called an offset move. That's part of the unload task.
Okay.
And if you want, you can turn that off. On the operator, there is there's an option to say don't travel offsets. So like if you look at the operator properties.
Yeah, travel offsets for unload load tasks.
Yeah, if you turn that off, then they walk exactly the same distance. That little offset move is just part of the load unload to make it look a little bit nicer.
Okay. Let's see here. There we go. Perfect.
Yeah, I didn't talk about that during the run-up because I didn't think it was important. But, if someone cares enough to ask, then I'm happy to point it out. But it's just part of the default, that default travel operation. That's part of it. That's like implied in the load and an unload.
Yeah, I just know if I have some people in my organization that if they weren't traveling the exact same
Yeah,
distance,
no,
the
that's
question
wrong.
would, yeah.
Yeah, it comes up in every model. There's always someone that says, that doesn't look exactly the way I expected, therefore it's invalid. I was like, okay. It's just an animation, but okay.
Yeah. All right, cool.
Good. Anyone else got it finished or just making progress through it?
Can we have a couple minutes more?
Yeah.
Sorry, I think they are working, but I keep receiving a lot of system error.
Let's take a look at what they say and see if they're really important ones to fix.
Okay.
Okay, so this is something that seems to be going on with your processors.
Yeah. But I didn't change anything.
Yeah, let's delete the text in the error console and just reset it and run it over again. I just want to see exactly when that happens. And when the text pops up, when the error throws, just be ready to stop the model right away.
Okay. Apologize, my laptop is running really slow.
It's okay. It happens. Okay. So something about this sort of error generally means that that there were other events that the flow item thought that it was supposed to be doing when another event took place. So I think it's because you have multiple load. You have a load task and an unload task for both of your operators, which is potentially dangerous because that's going to create events on the flow item for load and unload events. And so it could be that the flow item thought it was still involved in an unload when it got destroyed, and that kind of caused all this to happen. So this is sort of what I was mentioning before, that only one operator can physically load or unload the flow item. So the other one needs to just wait until the load and the unload happens before its token can move on. It's really dangerous to have a load in both of these task sequences that you have here and an unload in both those task sequences. And so you should only have one load and one unload. So you'll need to choose one of them to be the person who actually does the loading and the unloading, and the other person just needs to wait until the loading and the unloading happens. And this is really where you should be using things like Synchronize. Wait for event can kind of work for this, but Synchronize is more efficient.
Okay. Okay, let me try again.
Okay.
Thank you.
Mm-hmm. Everyone still doing okay?
Yeah, I'm just kind of stuck on the challenge.
Yeah, the challenge is actually pretty tough.
Because I got it working where, you know, it splits them up. I had to do it by weight, so like anything that was deemed heavy required to, but then I wanted to see how I could make that second operator not just stand around while the other one was bringing boxes over, and I couldn't do it.
All right, well, I'll go over it.
Okay.
So if everyone is ready for the walkthrough on like the base description, we can do that, and then I'll show you a way that you could do the challenge. Okay, so let's do the basic walkthrough first. I've already gone ahead and built the model, and I'm going to work through this much like how you would approach it if you didn't hopefully already know the answer like I do because I designed it. But the first thing to think about is, okay, we're going to have our boxes arriving every 20 seconds, which is fine, and then things will be sent from the queue round robin, which is fine. And so if we just run the model with what we have right now, we'll see the boxes alternate use of the processors, right? So processor 1, then processor 2, processor 1, then processor 2, just back and forth. And so the hard part of this is going to be asking my operators to work together on this problem, so that they can carry, so that one guy, one of my operators will carry the box physically while the other one functions as an escort in order to simulate the idea that both of these operators are working together. So I'm also just really quickly going to give them a load and an unload time. See if this new trick of the interface works, where I can, if I select them both, I think I'm supposed to be able to do both of them at the same time. So we'll do a 2, an 8, and a 5. Whoops. And if we check the other operator, yay, it did them both. Okay. So this is a new thing they did in the interface to make it easier to assign properties to the same object. So like, for example, since there are both selected in red, which you can do with a shift drag around the operators, when you choose an option like triangular, and then do a 2, 8, and 5, and then if I just like click off, you'll see like this little window is supposed to pop up that says 2 objects changed, but it looks like it didn't pop up. But it did properly assign the load and the unload time to both of the operators. So rather than having to go to both of them, if I select them both and then change it in the panel on the right-hand side, then it does the assignment of the load and unload time at the same time for both of them. So that's cool. And then to get rid of the red selected, just shift click in the grid and it turns off the red selection. Okay. And so, like I said, the first thing that I would do is to try and recreate the task sequence that you would need in order just to get one of the operators to carry the box, right? And then we'll use that as a starting point for adding in the behavior for the other operator so that we can kind of check and see how things go as we go along. So in my subflow, I'm going to have my start activity. And in my queue, I'm going to say that we are using transport, but our transport will be defined using a task sequence subflow. And so one of the first things I'm going to decide is how am I going to get the information for the dispatcher that I'm going to use into my subflow? Well, the option gives me a hint that maybe I should make a center port connection and call that dispatcher. But maybe I don't like the dispatcher label name, so I'm going to actually change this. I'm going to call this operator. But I will make the center port connection, and we'll do my red shirt operator first. So in my subflow, I'm going to start with a create task sequence. And this task sequence will be created onto my operator. And then my first step will be to travel to the from object. And then we will do a load of the item from the container. And then we'll do a travel to the to object. Now, keep in mind, too, that you can change these labels that come from the queue. If you don't like from object and to object, like I didn't like dispatcher, I called it operator instead. You can rename any of these labels to make more sense, but I just kept them the default except for the operator one, because that operator is not really acting as a dispatcher. She's just operating as an operator. So it makes sense to me to change the name. But if you don't like from object and to object, you can change those as well. And then we're going to do an unload. Oops. Unload the item to the to object. And let's also add in another travel. Let's bring her back home to the queue when all this is finished. So we'll say travel back to the from object and wait for further instructions there. And so then we'll finish that task sequence, and then we will finish the subflow. And so what we'll see there is our red shirt operator. She'll pick up the flow item after her load time. So you see that little hesitation for the load, and also a similar hesitation for the unload. Just simulates the time it would take to physically pick up that box and the time it would physically take to put down the box. So rather than having it happen instantaneously, we're using the load and the unload time. And that's triggered automatically by the load and the unload task. So if you have a load and unload time on the operator and you tell them to do a load or an unload task, they'll automatically delay for the time on their load unload properties. Okay, so this is just the basic behavior. It's actually a little bit better too, because I have that built-in travel that brings her back to the queue before she starts the next task sequence. So already I've kind of improved on things a little bit, where if there were no flow items in the queue, she wouldn't be waiting around at the downstream queues waiting for the next assignment. Okay, so now I need to figure out how am I going to incorporate operator 2 into this. So the first thing that I need is a split, because I get one token into the subflow that represents the flow item that needs to be transported. And so that one token, I actually need to split it into two so that I can use 2 tokens to give 2 separate sets of requests to my 2 operators. So I'm going to go ahead and bring in a split. And to kind of help organize things a little bit, I'm going to create a container over here. And I'll call this my primary operator flow. And I'll make a copy of this container and put it over here. And I'm going to call this my helper operator flow, because that other operator is just going to help my primary person. Right, so everything that we've defined in there is really for the primary person. So I'm just going to put it over there, and I'll make this look a little bit better as well with the connectors, just so that we can use the containers like this. So the first thing that I want my operator to do is to create a task sequence and to travel. Now I need another connection off of the split that will let me do the same thing, but for my my helper operator. So I'm just going to move that a little bit so it's a little bit easier to work with. That's going to connect to this flow as well. And so I need to create a task sequence in here as well for my other operator. And so this task sequence also needs to be assigned to operator 2. So my first task sequence is being assigned to my operator, which is whatever's connected on my center port connection. So I'm going to kind of stay consistent with the way I'm doing this. So I'll make another center port connection from the operator to the queue. And then on the queue, I'm going to add another label. And I'm going to call this helper. Well, actually, helper's maybe a little too specific. We'll just call it operator 2. And the value will be my second connected object, so that I have the first connection that goes to my red shirt operator and my second connection that goes to my yellow shirt operator. And so in my create task sequence, I can say that this is going to be created onto operator 2. And so the first step of both of those task sequences is to travel. And they both need to travel to the from object. Right, and so if we just kind of see what that looks like, when the flow item first arrives, whoops, it's going to be mad at me probably because I don't have the connector on the containers. Let me just put that on my finish. No, still mad at me. What's it mad at me for? Oh, okay. Let me just put that back the way it was. Okay, sorry about that. So now they both walk to the queue, and because my other operator has more task sequence to do, she's just going to keep on going. My other guy though created a task sequence. He traveled to the location, and then he kind of just finished out. So the first step worked pretty well, where they both will walk together to the queue right there. That's what I want them to do. I both want them to travel to the queue. So the next thing that happens is the load. Now, again, because the flow item can only be physically loaded by one operator, only my primary task sequence needs to have the load. So my other guy just needs to wait until the load is completed before they start traveling back to the queue. Now, the reason why for that is let's actually, finish out some of the different steps that the operator two needs to do. So they both need to travel to the queue. Good. They're only one's going to load, and the other one is going to say, well, when that is over, I need to be able to travel to the to object. And once I'm done traveling to the to object, I need to travel back to the from object. And I need to finish my task sequence. That's what the helper basically needs to do. But if I don't have any way to synchronize the two of them, watch what happens, where they both will walk together. Good. Operator two just takes off, because I don't have anything in there that says, hey, you need to wait for the load to finish, and you need to wait for the unload to finish before you can go back home. So these task sequences are happening completely independent of each other, and it's going to cause some weird behavior, because I don't have anything that tells my helper guy that he needs to wait for the primary to finish doing the load and the unload. So this is why I need synchronization points in my coordinated task sequence, so that I can know that operator two, if he doesn't have something to do like doing a load or an unload, that he needs to hang out and wait for the primary to finish doing the load and the unload. So now he's just sort of traveling all over the place, and it looks really weird. So I'm going to add in a step that says that once they've both traveled to the location that they need to go to, I'm just going to kind of move all this stuff down out of the way. They need to synchronize with each other, because I want to know that both of my operators have arrived before I allow the load to take place. So I'm going to call this synchronize, wait for both operators to arrive at the queue. Okay, and so I need a connector in from my primary person. So I'm going to make sure that she is on the first inbound connection. And then this connection that was going to the travel, I need that to come into the synchronize. And the reason why I have this synchronize step is because what if they are traveling from different places, right? So like say operator one or my primary operator is like way over here. I need a way to make sure that I know that they're both present so that the load can take place. Because if they're at different locations or they have different walking speeds, I want to make sure that both operators have arrived. So by putting the synchronize after the travel, it's a way for me to say, you can't continue your flow until both of you are present, both of you have finished doing your travel. So that's what the synchronize is doing for me here. It says, wait for everyone to arrive. And then once they both have arrived, then we can do a load. And again, I'm making sure that my first outbound connector on the Synchronize is for my my primary operator, who is represented by the token that comes out of the first split connector. And while that load is going on, I actually want to make sure that my second operator doesn't just start doing its travel. So here is another Synchronize. And so again, my first operator comes into the Synchronize to say, yep, I finished doing my load. And my helper operator just goes right into the Synchronize and waits for the load time to finish. And so this Synchronize is saying, essentially, wait for end of load time. And once that is done, then they can both travel. So if you see the way this looks now, if I hit reset and run, so operator 2 got to the queue first. Operator 3 is still in transit, and she's the one I've essentially flagged as my primary. So he is waiting for the other operator to arrive. And then when they both arrive, now we can do the load. And the other operator continues to wait until the end of the load time, so he doesn't just take off and leave the operator behind. And then once they pick it up, now they can both start traveling to the destination. Now, I also want to make sure that I synchronize for when they both have arrived. So if I want to be like really, really careful about the way that I do this, I'm going to say that no travel after the Synchronize. So I'm just going to put those in line with each other so I can see those. Give myself some more room in this container. So here's another Synchronize that is going to say that we want to make sure that everyone has arrived. Wait for team arrival at 2 object. And I'll make my connector in there, and then I'll move this connector to in here. Try and make it as straight as I can. And once they both arrive, then we can do, we can do the unload. And the other operator needs to, again, just sort of hang out and wait for the unload to finish. So we're going to bring in another Synchronize. And this time we're going to say, wait for unload to complete. And again, the first connector in is for my primary operator. Second connector is for my secondary operator, my helper. And then once that's done, then we can travel back home. Where they both finish their task sequence and they finish the subflow. So now they walk to the queue, they wait for each other there, they load and then they travel, then they unload. Oh, I made a mistake. So looking at the Synchronize, you see how my connectors don't match. And this is something they have to look out for when you're doing a synchronize. I was afraid I was going to do that by accident. So inbound 1 lines up with outbound 1, inbound 2 lines up with outbound 2. This is one of the reasons why I like setting up the synchronize activity like this, where it like spans across the flows that I'm synchronizing, so that when I click on it, I can easily see if the connections don't line up. So right here, the second inbound connection to the synchronize, actually, I meant that to be the first. So I'm just going to come to this and say that the 2 rank is 1. So it sets that up correctly. Because before, my yellow shirt operator was doing the offset travel, and I really wanted the red shirt operator to make sure she was doing the loading and the unloading, because otherwise I can get like some weird behavior out of that. I want to avoid anything strange. Okay, so I used a lot of synchronizes in this for safety for the most part. I mean, you could probably get away with not having the synchronize that says wait for both of them to arrive to the 2 object. Probably could get away with that, but you would definitely want to make sure you have the synchronize that says that they both have to, you know, stay put during the unload time. And the unload task is going to do that fine for the primary operator, but the secondary operator will need to sit in the synchronize and wait for the other operator to finish before they can release their tokens and move on to the next step. So that's the main description, using the task sequence activities plus adding in synchronizes to be able to allow my operators to synchronize along the way to perform this coordinated task sequence. And again, it's just simulating that idea, right? You watch them and you can easily tell that only one operator is actually carrying the flow item, right? And that's okay, because what we're really looking for is making sure that the behavior mimics the results of 2 operators working together to carry a single box. So that their resource utilization, like any statistics that show them both being used, are being properly accounted for. Okay, so what about the challenge? So I have a model already built that that does the challenge, and so you guys have a copy of this in the download section. So this is called Coordinated Tasks, Chapter 9. And you'll notice that in this model, I have 2 different subflows. I have a subflow for the main part of the model description, and then I have a challenge subflow that I can turn on and off. So in this model, with the challenge subflow, the first thing that I needed to do was I needed to know the difference between a flow item that did need 2 operators and a flow item that didn't. And so I did that with just a label where I just gave them a different type. So it's like 50-50, where type 1 means that you do need help, and type 2 means that you don't need help. So up here in my decide activity, I'm basically saying if come on UI, if the type of the token is type 1, if that's true, then I need help. If the type is not 1, then I don't need help. And so the decide activity says, if you do need help, you do the split and basically this big thing that I'm calling the cooperative flow. And if you don't need help, then I have a single carrier flow. And this is all part of the same subflow. So I'm using a resource here that is referencing a group of operators. There's a couple of different ways to do this. I chose to do it with a group. And the token that represents the flow item will acquire either a single operator to the single carrier flow, or it will acquire 2 operators in order to do the cooperative flow. And that's the only change that I really made here was this this thing that says that you're going to acquire a member of your operator team. So in the toolbox, I have a group of operators consists of operator 1 and operator 2. And so my resource reference just says reference the group of operators. So when you do an acquire, you'll get a member of the team, and then you'll tell them what to do by creating the task sequence on the thing that you acquired. And then you'll release the operator when you're done with your task sequence, and then you finish the subflow. And so when you watch it run then, a red box calls for both of the operators. And a green box will require just one operator. So they're going to work together on that red box. And then when we get back to the queue, there happen to be 2 green boxes already in the queue. And so now each of them are going to do a single carrier flow where they each carry a green box. Because I just created the single carrier flow to say, yeah, just travel, load, travel, unload, and finish. And so if there is something that requires both of them, then they'll work together. But if there's something that only requires one of them, then they each get to grab a green box. Because those flow items are trying to acquire a task executor to see if there's an operator available to do that work. And if there is, then they get to go in and do it. And because I have the resource team looking at the members of the group, then that allows me to acquire both operators if there's enough work to acquire both operators. And so this is actually kind of an interesting situation right now where there was a green box that operator 1 could carry, and now the next flow item is a red box, and we don't have the other operator available yet, so we have to wait until this guy finishes carrying his green box. So this green box is being represented by this token in the single carrier flow, and now we have another token that is already in the Synchronize that says, I'm waiting for my 2 task executors to arrive at the from object. And there's another token here that's trying to acquire the second operator, but it can't because he's in use. So when he drops off his flow item, now this token is allowed to acquire the operator. That tells him to go back to the from object, and now we can do the cooperative flow again. But it held the other operator in the Synchronize while he waited for his teammate to come and help him carry the red box. So with the way that I have it set up, it works pretty well, even if it's just a random chance that you need help, and sometimes you do and sometimes you don't. And he's just carrying the boxes first come, first serve. So I'm not doing any sort of like prioritization that says, well, if there are cooperative boxes, maybe you do those first, or if there's single flow boxes, maybe you do those first. You could do that with the way that you acquire things from the resource. You could like use the queue strategy and the queries of the resource like you would do on a list to decide, well, which of the tokens are more important to the resource? Is it more important to do the green boxes, or is it more important to do the red boxes? Right now, it's just first come, first serve, but you could use some of these advanced options on the resource to handle that. Or you could also use a list. You could use a list as a way to acquire the operators and decide like what is the best thing to do next. But I'm doing it with a resource because you can kind of use a resource like you'd use a list if you want to. A lot of overlap between the resource and the list if you're using a team of objects as the resource reference on the resource. Becomes very listy in that configuration.
So the challenging part about the challenge really is knowing when one of your teammates is doing a single flow so that you wait for him to be available so that you can work together. And knowing the difference between a flow item that does need 2 people versus a flow item that does not need 2 people.
Yeah, I think because the slide said use a list, I was kind of focused on that, trying to figure it out that way.
Yeah, I just barely switched it over to a resource like in the last few weeks, because I was looking at it, I was like, this is maybe overkill for the list. I could do the same thing with a resource and maybe it'd be simpler. So I need to update the slides to say, use a shared asset, either maybe a list or maybe a resource, you know, so you can try it either way, because either way works well. It just depends on which way you'd want to do it. But a shared asset to know when an operator is in use really helps the cooperative versus single carrier flow, you know, work the right way. Okay, any questions at all?
I'm back. I do have a few questions, but I guess after everybody else's question. If somebody has some. Because are you going to show anything else, or it's
Nope, this is the end.
okay.
I declare you all to be trained as of this
Okay.
model.
All right. Hey, I lose the explanation about the split, although it looks like pretty straightforward. But what's the difference between using a split or a batch that receives 1 and becomes 2?
Yeah, well, there's basically 3 activities that allow you to create more tokens from a single token, right? You've got the batch, you've got the split, and you've got create tokens. There are 3 different ways to say take a token and make more tokens. And they just have slightly different ways that they handle making additional tokens. Like the batch and the create tokens allow you to say, create a number of tokens equal to a label on the original token. And when that sometimes is useful. The split says that the number of outbound connections tells me how many tokens you want to make.
Okay, gotcha.
So 1 token goes into a split and tokens equal to the outbound connection count go out. With the batch, you get to just say 1 token comes in and as many tokens as I want come out, either based on like typing in a number, looking it up from a table, looking at it up from a label, and create tokens does something similar. The difference though between batch and create tokens is that all of the tokens that were created by the batch stay in the same flow where the batch is located. So 1 token goes into the batch, multiple tokens all come out, and they just go to whatever activity is connected to the batch afterwards. Create tokens allows you to specify a different destination for the created tokens versus the original token.
Okay.
But it doesn't require an outbound connection. You can just say, go to that activity over there, like a delay or a start activity, or any activity really can be a valid destination from the create tokens. So it's just like varying levels of control. Like the split makes a bunch of assumptions about how it's going to work, and the batch makes a few assumptions about how it's going to work, and the create tokens make some assumptions about how it's going to work. And so it's just a matter of which of those 3 methods falls more in line with how you want things to work.
Okay. Is there any well, I guess I will answer my question myself, but like I see that a split I can create as independent tokens or siblings or child.
Yep.
The sibling and the child looks like pretty much the same, isn't it?
Not really, because a child token means that the original token that went into a split becomes the parent of the new tokens. A sibling means that if the original token is a child of someone else, then the created tokens now have the same parent as the original.
Okay, a modern family.
So that also means that, because remember, like one of the big things about parent-child relationships is like the accessing and sharing of data from parents and children. And so if you have a token that is a child of another token, and you create any additional tokens from that child as independent tokens, then those new independent tokens don't get access to the parent data of the original token. That's super confusing, I know, but it's the way the relationships work. And so if you make new tokens from a split that are siblings of the original token, that means that the new tokens now have access to the parent information, that goes up a generation. It goes up to the parent labels, which can sometimes be useful because a lot of times when you're creating all these additional tokens, you want the newly created tokens to know about data on other tokens that they originated from. And so the relationships allow you to access that information, and that's why they become important.
Okay, can I share my screen real quick? I just want some insights from you, and maybe how would you do it? Not, I mean, basically just a thoughts on it and things that you would do differently. I see that the examples that you gave, like using the model, the 3D objects, and the process flows, really helps out a lot of things. But I try to do a way that I do only process flows. And I know that here, for example, all of those are the same activity basically, require two resources. And the way that you did the link of the resources or being able to, let's say, making sure I'm not using more than one resource at a time is you created the object, and the object basically it's a limitation, right? I mean, you just link with a resource to create a task, and when the task is finished, then the task executor is released. Here, I try to do a way which is basically this is a queue, and the queue can only receive 15 items at a time, and after received, it has to wait 8 hours to cool down, and then it's free to start again. Kind of worked some way, I have 4 queues, and actually, this is the available queues, and this is the non-available. So sometimes I use two queues, but sometimes once. But it feels like I'm putting too much programming and things like that to this model. Maybe there's a simpler way to do that. The whole operation, just to give you a basically overview, is like create a source. Some of the source will share the same queue sometimes, but it will be split by different types. So you cannot mix types here. A resource, which is imagine like a truck, comes in and drop in that queue. And then when it's clean, wait for like after the cooldown period, a loader comes in, get the material, load into this processing plant, and then I will call another loader and a truck to perform a task. The truck will load the loader will load the truck. The truck will travel. The loader will be available again. Is that how would you do it? Would you mix with the model? Is kind of optional, or I mean, what are your basic thoughts or suggestions?
Well, I mean, my personal style of building models is to lean more heavily on process flow. So I would probably take an approach that is more similar to what you're doing, just because that's the way I tend to think about how I tend to think about solutions to problems. Is I want to control every aspect of it.
Mm-hmm.
So yeah, but it's just a style choice. someone else might look at like a description of your model and choose to do it a lot more with like the objects and stuff like that. But yeah, I would probably be doing something more like what you're doing right now if it was my project, just because that's my style, not because it's better or anything, but just because it's my style.
And so like to represent a queue, like I did here, I just put a limitation of the zone. As a number of items that can come in is 4, the maximum. I don't know, where is it? It's probably here, base, maximum content 4. That's
so you get those, because you get those 4 things in the queue, and then you pull them when it's okay for them to leave the queue. So like the pulling from the list becomes like the signal that it's okay for them to continue their flow, right? And so that's a fine way to handle that.
Yeah. Okay. So I guess I'm in the right path, right?
Yeah, I think so. Yeah, there's just a couple of things that you could, you could consolidate some things with subflows because you're recreating like a lot of similar behavior in a lot of the same places that you could probably use some subflows to shrink down the number of blocks of logic. But, again, that's mostly a style consideration rather than a functional consideration.
Okay. One last question would be, how can I depict the opposite of this one? Like, for example, I started with 4 and I have 3, sometimes 2. I want to depict 4 minus the number that I have in here. Like 4 minus the number that I currently have at the zone. So that's how much is being used actually.
You'd have to use a stats collector to do that. Stats collector is even more advanced stats gathering tool than the zone, where you'd want to, just like you said, have the inverse. So like if you have, you're more saying like there's one thing available rather than like one thing present, or something like that.
All right. Regan, I really appreciate it. The training was very, very good. In my opinion, I learned a lot, especially about this, the process flow. I think it's a really good new tool to use and speaks more the language of Haskell. Thank you. Thank you so much for your time this week and your patience to go through our questions.
No, thank you, all of you, for hanging in there. I know it's it's a less than ideal learning format for something like this. It's a lot more fun for me when it's in person, and people tend to get more out of it when it's in person. So hopefully one day we get to go back to doing things that way. But thanks everyone for hanging in. It's tough to learn new software like this, and it's especially tough to do it in this format. So I appreciate you guys sticking in there and building the models and giving it a try, asking questions. It's much more fun for me when people ask questions. So hopefully you feel like you got something out of it. And like I always like to joke, I declare you to be trained. I bless you all as trained FlexSim users.
I will put in my resume.
Thank you, Reagan.
Thanks a lot, Reagan.